share my screen while we're okay, it looks like the participants thing stopped changing. Oh. We'll give it one more minute and then we'll get started, everyone.
So is there a way to communicate, aside from talking, is there a, where do I put stuff in the chat? Like, I just put stuff in the chat?
I will defer to one of the ISBA people about that, but I think you can just put it in the chat.
Okay. I'm going to throw in the link to the materials.
All right. Sounds good.
All
right. With that being said, I'll share my screen and we can get going here. All right. Can you see this? Tony, they can't talk, so can you confirm that you can? Okay. All right. Well, with that being said, let's get to it. So first of all, thank you everyone for being here. This is a really awesome turnout for the short course, and we're really excited to have you all here. Obviously, we wish that this could have been done in person in China, but it's 2021, so we will be Zooming again for this conference. But we hope that you still enjoy this and get something out of it. So my name is Joseph Antonelli. You can call me Joey. I'm an assistant professor of statistics at the University of Florida. And with me today is Antonio Linero, who's an assistant professor of statistics and data science at the University of Texas at Austin. Okay, so today's short course obviously is going to be about high dimensional Bayesian modeling. But before we get started, I just want to run through some sort of preliminaries. I believe everyone in the audience there, well, first, this is being recorded, so if you have to leave or if you miss a part, no worries. You should be able to go back and watch it later.
There's a chat asking if Margarita wants to know if they're the only person who can not hear anything. I think people can hear, right? I can hear you, so.
Yeah, so if anyone in the chat, okay, so people can hear, everyone can hear? Okay, I think it might be an individual problem, unfortunately, for the first person who put the message in there. But please send messages in the chat if you can't hear us. That would obviously be a big problem. All right, so let's get back to it then. And then, Tony, you can keep track of if I'm not coming through clearly or lagging or something of that nature. And then people in the room, feel free to message us if anything's going on, because it's hard for us to tell. Okay, so, and Alan, I'll get to your questions here in a second. So briefly, just to give you a rundown of what this course is going to be like. So it's going to be roughly 4 to 4.5 hours. I will talk for the first half on sort of vanilla high dimensional Bayesian modeling, introduce spike-and-slab priors and talk about them in the more simple settings of linear regression. And then Tony's going to take over at the halfway point and do teach us all about some really exciting stuff that he's done working with tree-based models and Bayesian modeling in high dimensions. So we'll have a couple breaks throughout. So I'm going to crank through, about an hour to an hour and a half, and then we'll take a 5-minute break or so. We'll go through a little bit of R code, and then I'll finish up my section. Tony will take over. We'll take maybe one more 5-minute break. We'll kind of cut it up into thirds. So we'll have a couple breaks in there. I know people are asking about that in the chat. So we should be set there. In terms of you guys being able to communicate, we can't hear you. The audio is disabled. But if you have any questions, feel free to put them in the chat or the Q&A. If it's something simple that can be addressed just with a comment in the Q&A or the question, Tony can take care of it while I'm lecturing and vice versa. If not, it's something important, we'll stop and we'll talk about it in more detail. Okay, so I know it's a bummer that we can't talk to each other, but feel free to leave comments if you have any questions as we go. Okay, so with that being said, let's get started and let's talk about the fun stuff. So the first question, of course, is why are we all here? So hopefully you guys are all at this conference because you're interested in Bayesian analysis. And hopefully you're in this short course because you're interested in learning more about high dimensional aspects of Bayesian analysis. So Bayesian analysis, high dimensional sort of, not just Bayesian analysis, but analysis in general, has really exploded in the last couple of decades. And there's really a number of reasons, and I don't think I've listed them all here, but there's a number of reasons for this sort of expansion and interest in this topic. The first is that, especially for Bayesian computation in high dimensions, we've had major advances in computation in the last few decades. So while I could have given this lecture 30 years ago, we wouldn't have been able to actually implement any of these approaches because, if we actually want to estimate these parameters and we want to do MCMC in high dimensions, it becomes kind of burdensome, especially in high dimensions for Bayesian inference. And, obviously that's been resolved a little bit to this point. And so these methods are actually able to be used. There's also an increasing number of large data sources. So, omics type data sources like genomics and proteomics and others. It's pretty common these days to have data sets where thousands or even millions of features are measured on each individual. So we can think of imaging studies like a brain imaging study where we measure we have voxels of a brain. Medical records like electronic health records can become high dimensional pretty quickly once those data sets have been cleaned up and mined for covariate information. I think another reason why these techniques have become popular why they're so widely used now is that there's been a lot of methodological development and advancement in the last couple of decades, particularly the last decade, in these techniques, sort of broadening the scope of questions that can be addressed with these types of models and when we can use them, right? So I think, I personally believe that even if you don't actually use these things in your own research or are trying to use them yourself, it's important to have a working understanding of these because they're the kind of things that they show up regularly. When you're reading papers, these ideas come through quite a bit these days. And I think it's important to have a good grasp of how they work. Now, I'm obviously a little bit biased here. I'm teaching a short course at the ISBA conference, but I think that Bayesian approaches are really useful in this setup. And a lot of the reasons that Bayesian inference is really useful in high dimensions are sort of the cliche reasons that people always say that Bayesian inference is useful. But I think that those reasons are more pronounced in the high dimensional regime where doing inference can be very difficult, right? So for instance, accounting for uncertainty is very easy and natural within the Bayesian paradigm. We're going to see in today's lecture that introducing nonlinearity into these models and growing their complexity is fairly straightforward. Two things that we're not going to see today, but could be very useful within the high dimensional regime, and it would be easier from a Bayesian side of things, would be to introduce more complexity into your models like hierarchical structure, handling missing data. I don't know how you would handle missing data within frequentist high dimensional models, but in the Bayesian framework, it's fairly straightforward how to impute that and account for its uncertainty. Right. So just a little background. I mean, we don't have time to talk about the sort of frequentist estimators in high dimensions. But these, generally speaking, a lot of them don't provide inference, meaning they can give you a point estimate of a quantity that you're interested in, but you cannot get a corresponding confidence interval out. You don't get a standard error estimate out of these models, right? So that's obviously problematic. In some cases, it might be useful to just simply come up with a point estimate. But I think, myself as a statistician, in many settings, it's almost useless to have a point estimate with no corresponding measure of uncertainty, right? And there's been work done to alleviate this. I don't want to completely, disregard this line of research. There's been some really interesting stuff done at improving inference and accounting of uncertainty in these frequentist penalized estimators. All right, so I've listed a couple papers here that are sort of seminal papers in that regard, and there's been a sort of ton of literature since those have come out trying to alleviate some of these issues and address some of these problems. But generally speaking, these approaches to inference are very specific to certain models, and they rely on very, very strong assumptions. I'm not here to say that the Bayesian approaches in high dimensions don't also rely on some assumptions, but I think some of these assumptions are to doing inference are very strong, and maybe we don't have to rely on them as heavily in the Bayesian paradigm. So for that reason, I think it's a very useful thing to model things in high dimensions from the Bayesian point of view. So I hope you can take away certain things from this course. There's going to be a lot thrown at you in the next few hours. But at the high level things that I hope you can do are that you come away understanding some of the prior distributions for high dimensional models and some of the computational difficulties that might come with them, and therefore how you might go about coding up your own MCMC if you had to, right? This is, I'm not an expert in Stan or WinBugs or those sort of software that can do MCMC for you, but in a lot of these settings, they wouldn't necessarily work with these high dimensional models that embed variable selection into them. And so you might have to code these up yourself. So we're going to spend some time talking about how you actually code these up, how you get the MCMC working. And then we're gonna wrap up with, and say wrap up, we're going to spend half the lecture talking about some more complex models, how to introduce nonlinearity into your models, and how to understand these tree-based models that Tony has talked about. So there is a question I see in the chat that can choosing a prior be seen as a strong assumption on a model? Absolutely, right? So I don't want to say that Bayesian inference comes with no assumptions being made. And the fact that you have to assign a prior distribution, especially in high dimensions when it's difficult to have prior beliefs about parameters, that is, of course, a modeling assumption as well. So there are assumptions that are unique to the Bayesian side of things that maybe aren't there for the Frequentis side of things. So I hope I didn't overly strike that. I mostly wanted to say that Bayesian inference can be very useful for accounting for uncertainty in high dimensional set, but many of the same issues of any Bayesian analysis, such as choosing a prior, come into play. And we're going to talk about those today and sort of how to choose some standard ones that seem to work reasonably well. Okay, so moving on. All right, so this is a little disclaimer here. Tony had a little bit of a beef with this disclaimer when I showed it to him, but I'll say at least I am not an expert in all aspects of high dimensional Bayesian inference. I've used these models extensively in two different areas of research. I've used them in environmental health, and I've used them in causal inference when the number of confounders is really relatively large. But there are so many different types of high dimensional models, and I am not an expert in every single one of them. Tony maybe is, but he can talk to you about his work in the second half of the lecture.
No, I was just saying that I have faith in you. I think you're underselling.
Oh, well, I appreciate that.
I'm not an egomaniac.
It's to save ourselves here. I will say also, in addition to this, even though I don't know everything about high dimensional Bayesian models, we also don't have time, even if we did know everything, to cover everything, right? So we were mostly going to focus on a couple things today. In my portion, we're going to focus on spike and slab prior distributions, right? We're going to talk about how to use these prior distributions within regression models to reduce the parameter space, to find which variables are important. We're going to talk about sort of the ins and outs and the intricacies of how to use these, how to computationally how to use these prior distributions as well. And Tony's going to talk about his work, which is really interesting on tree-based models. And so sort of I'm going to be making some strong assumptions, some modeling assumptions throughout, and then Tony's going to alleviate those with the second half of the course. Okay, but of course, this is only a subset of the stuff that's out there. So for instance, one big thing that we're not going to talk about are continuous shrinkage priors, which have received a lot of attention in the high dimensional Bayesian inference literature in the last 10 years or so. I'm sure there are others. We have, if you want references to those or us to point you in a direction for where to read more about those or any other topic within this scope, just let us know. And we can probably point you in the right direction. But again, we'll have to leave some stuff out. So here's kind of a map of what we're going to do today. So we're going to start simple. So starting on the left here, we're going to start with the linear regression model. Okay, so we're going to assume that the relationship between an outcome and our covariates is this additive and linear function. Right? And this is where I'm going to spend most of my time talking about it. We're going to talk about the sort of finer details within this simple model. And then we'll talk about how to extend it to alleviate linearity assumptions. And we'll see that a lot of the same ideas that we learned in the linear case apply to this setting as well. Right? So, we can learn about a lot of these sort of intricate details in the linear setting and then extend them to other settings quite easily. And then we're going to take a different turn when Tony takes over, and we're going to talk about making no assumptions of additivity or linearity on the model using these tree-based models. So the reason we're going to start with the simple linear models is we're going to introduce the prior distributions that one could use, right? We're going to talk about one thing that's sort of a burden to implementing these approaches is that the hyperprior choices are very important. And there are some sort of set ways to do it that work reasonably well, but it's important for us to understand the importance of these choices and what implications they have. And then we're going to talk about how to sample from these models. Okay, so after that, we're going to then try to alleviate these assumptions of this model. We're going to go right on the diagram of the roadmap. We're going to try to drop the linearity assumption first. So I'm going to talk to you about a couple different approaches to dropping the linearity assumption in these high-dimensional models. So one is going to be a grouped variable selection with basis functions, which is very similar to the linear approach, fully parametric model, just in high dimensions. And then I'm going to talk briefly about how to use Gaussian processes, which is a nonparametric Bayesian formulation to this problem as well, and how they can also be used within these high-dimensional scenarios. And then we're going to finish the course, and by finish, I mean half the course will be on tree-based models. And I can tell you that these things work extremely well. I personally have used some of the software that's going to be talked about in the second half. When I was working on another paper and I was using it as a competing approach, and I just couldn't beat it. It was just always working extremely well. So I think it's really important to understand these tree-based models as well, as they have shown empirically to be very strong approaches. Okay, and so then throughout, we're going to try to give you examples. I'm going to have some R code to implement a simple Gibbs sampler in high dimensions. And then in Tony's portion, he's also going to have code sort of embedded throughout his slides that also, oh, I forgot to mention, you might have to go scroll back in the chat now because there's a lot of chat posts. But at the beginning of the chat, Tony posted a link to a GitHub repository, and that has all of the stuff that we're going to be talking about today. So that has all of our slides. It has the R code that I'm going to go over. It has R code that he's going to go over as well. So anything that we do in today's lecture, you can do if you go to that GitHub webpage. All of those materials should be there. So again, feel free to. It should be at the top of the chat. If you can't find it, just shoot us a message and we can post it again.
I think they have a much shorter chat history than we do, because we see everybody's stuff. Let me say something if you don't see the links that should have been put out, or maybe if you joined late, I'll put it in again.
All right.
But if you might want to get started if you're interested in coding along. Okay, the ISBA people put it out in the chat. Some of the software can be a little bit tricky to install. If you go there, there should be a folder called BART materials, and then the first one of those is called install. So the first of the R files, and that has a list of things that you will want to install if you want to follow along. And yeah, they can be a little bit tricky to install, but that's just if you want to to follow along. But everything, as far as the BART stuff that we'll be talking about, you can do everything using just the first package if you're having problems with the other ones. All right, so I'll hand it back over to Joey.
Great. Yeah, so again, though, all that stuff is there. And if you have any difficulties with any aspect of it, or you don't know where to find something that you're interested in from the slides, just shoot us an email and we'd be happy to send it to you directly. But hopefully it's all reasonably clean enough in the GitHub that you can find it. Okay, so moving on. So let's really get to the meat of things. So enough about the roadmap and what we're going to talk about. Let's actually get into the details here and talk about how these things work. Okay, so we're going to take a pretty standard notation here. So outcome of interest will be Y, X are our covariates, and we're really interested in understanding how X relates to Y. And in particular, one interesting question for us in this scope, in this high dimensional world, would be which of the X variables we might think that some number less than P of them is actually important for predicting the outcome. We want to know which of those, we want to be able to identify those. So N is our sample size. And our goal throughout, we're going to stick to the linear regression setting, but most of these ideas apply instantly to generalized linear models and some more complex settings. But for just simplicity and for brevity, we're going to stick to the case we're interested in estimating the mean of Y given X which is equal to some function of x. Okay. Our goals throughout are going to be twofold. We want good prediction performance, and we also want to identify the important predictors, right? So there might be situations when you're really only interested in one or two of these goals, right? But we're going to kind of be working on this assumption throughout that we're interested in both of these goals. But maybe with an emphasis on identifying the important predictors, but we'll get to that as we go. And then lastly, just for some notation's sake, we're going to let the number of important predictors in X, so the number of the covariates that actually affect the outcome, conditional on the others, is Q. Okay, so we're kind of working under the assumption that Q is less than P. All right, let's move along. Okay, so in high dimensions, people can mean a number of things when they say high dimensions, right? So that people are typically referring to situations where P is bigger than N. So the number of unknown parameters is large relative to the sample size. We're not going to spend really any time talking about theory today or asymptotic rates or posterior contraction or anything of that nature. There's a lot of literature about that on these models as well. But so in that literature, people typically assume that P, the dimension of the covariate space, grows with N. But for the sake of this short course, I think more what we're interested in getting at is we're going to be thinking broadly in terms of situations where you need to do some sort of dimension reduction, right? Where high dimensional models can help you because your parameter space is high enough that you can't just simply use standard approaches. So, let's say that you had a sample size of 100 and you had 90 covariates. Technically, P is not bigger than N in that situation, right? You have more samples and covariates, but the numbers are very close. And I would argue that you still need to do some sort of dimension reduction, right? And so we're going to be kind of talking broadly about situations like that, where using shrinkage or sparsity-inducing priors can help you relative to approaches that don't do those things, that either will fail completely or won't work very well practically, right? In addition, as a situation that one might be interested in this is, even if you don't need it, you're interested in learning which predictors are important, which ones affect the outcome, and these can be very useful in that regime. Okay. All right. So I think everyone here is probably reasonably familiar with the linear model, right? So we're going to just stick to that linear case for the basic concepts of applying these models. Okay, so we're going to be working under this model, just the standard linear regression here. So we're going to let our function, our y, be a function of the covariates, but it's this additive function, right? So whenever I say additive throughout, I just mean that the effect of one covariate on the outcome does not depend on the values of the other covariates, right? So there are no interactions between the covariates in this model. And right now I'm assuming that the relationship is linear, right? That each covariate has a linear effect on the outcome. And then for now, we're assuming that the error variance, or the error, is normally distributed with some variance sigma squared. But we're not going to focus too much on this. Anything that we talk about today basically immediately extends to generalized linear models, right? So if you have something that looks more like this, you have a link function, this function of the mean, you can write that as this linear predictor. Logistic regression, probit regression, Poisson regression, anything that you can think of that falls within the GLM framework, these things would apply immediately, right? So in terms of computational aspects, things might be a little different, though for some of the standard link functions, there's pretty easy computational tricks to make all the computation effectively the same as for linear regression by introducing some latent variables. We're not going to talk about that today, but my point is to get away that all these ideas apply almost immediately to that more complex setting. All right, and so then if Q here, remember Q is the number of important predictors in our model. Well, in this linear model, that would be the L0 norm of the true regression coefficient vector, which is just the number of non-zero regression coefficients, right? And these are the ones we want to identify. We want to be able to identify which of these betas truly is non-zero, right? And so we're hoping that our models will be able to help us in that endeavor. Okay, right. So we're being Bayesian here. We need to assign prior distributions and learn the posterior distribution for all of our unknown parameters in our model. So in this model, we have two unknown parameters. We have beta, this high dimensional vector of regression coefficients, and sigma squared, right, the residual variance. So we're not going to spend basically any time talking about the residual variance, sigma squared. because you can just use standard prior distributions to update sigma squared. So I say here you can assume it's fixed. I would never assume it's fixed. Of course, in any analysis, you don't know what the residual variance is. But for the sake of discussion, you can treat it like it's fixed, or you can just assume that we're applying some standard prior distribution for sigma squared. So in the code that I'll go over later today, we're going to use a standard conjugate inverse gamma prior for sigma squared, a pretty standard approach to handling the residual variance. But all these ideas apply regardless of what you do with the residual variance. So what we're really going to focus on is talking about how to assign prior distributions for this regression coefficient beta. We want something that works well when the covariate space is high. So when P is large, right, potentially even larger than the sample size. We want to identify which of the covariates has an association with the outcome. So which of the true elements of beta 0 are non-zero. And we want something that can be implemented relatively easily computationally, right? So we'll see is that the R code that I'll show you today is one of the simplest ways you could implement a Gibbs sampler for these types of models. And we see that it converges, it sort of runs relatively quickly, right? So, but we want prior distributions that have that feature that we can sample from easily. All right, so this is an important slide, as this is sort of the prior distribution or some variation of this prior distribution is what the first half of this course is going to sort of be based on. Is prior distributions that look like this, right? And these are called spike and slab prior distributions, if you've never heard of them before. But I'll go over each bit of it here in a second. And I think they're fairly intuitive, right? So first, gamma j here. Gamma j is a 0 or a 1, right? It's a binary variable, essentially indicating whether that particular covariate j, is important or not, right? So if gamma j is 0, then the prior distribution for beta j is this. Right, this second part goes away when gamma j is 0, and you're left with this, which is just a point mass at 0. Okay. However, if gamma j is 1, which indicates that that covariate is important, then the prior distribution for the regression coefficient is a normal distribution with some variance, which we'll denote with sigma squared beta. Sometimes you'll see people put the residual variance in here as well, so the variance will be sigma squared times sigma squared beta, but we're just going to stick for this for simplicity. And then gamma j is just a Bernoulli random variable. So there's a Bernoulli prior on it with probability tau. Right? So this is the probability that gamma j is equal to 1, or the prior probability that particular covariate j is important. Okay? And so we assign independent priors for each of the p coefficients, right? Each coefficient gets this same prior, right? They're independent of each other. Okay. You could alternatively express this prior distribution as follows. If you summed up over the gamma j's, so you summed out or integrated out the gamma j's, you get the prior distribution for beta j is a mixture between a point mass at 0 and a normal distribution with variance sigma squared beta. And the mixing proportion for this mixture distribution is tau. All right, so what this prior essentially is doing, though, is it's saying, you know what? I believe a priori that some regression coefficients are going to be unimportant. Some are going to have value 0, right? And that's given to you by this, what's called the spike. It's a spike at 0, right? And then I believe that a subset of those covariates are important, and therefore, you know, they have some non-zero value, which is denoted by this slab component, right? So the important predictors can be given in this slab component here. So we're going to assume that it's a normal distribution, right? But any distribution, any continuous distribution would apply here. There are good reasons why one might want to use something like a Laplace or a Cauchy or something of that nature that has wider tails. But we're just going to stick for simplicity to the normal distribution case today. But sort of any continuous distribution that assigns positive mass to the real line would be fine here. Okay, so this was really kind of first introduced in linear regression in this seminal paper by Mitchell and Beauchamp in 1988, where they introduced this idea of a spike and a slab prior distribution, where the regression coefficients come from this mixture of something very close to 0 and something that's more diffuse. Right? That's the overall idea of the spike and slab, is that you have a mixture of two distributions. One is very close to 0. In our case, what we're going to be using today is that it's exactly 0. It's a point mass. And then the slab is something more diffuse that allows for things to have values farther away from 0 and therefore have important associations with the outcome. right? And it acknowledges this fact that we believe that some of them are not important, right? Some of the covariates are not important, and therefore you have this component of the mixture that allows for some of them to be exactly 0. So we're going to focus on that form of spike-and-slab prior distribution, but that is not the only one. There are many variations of it. A very commonly used one is the continuous spike-and-slab prior distribution, introduced in George and McCulloch in 1993, another very seminal paper in this literature, which is essentially the exact same prior distribution, but the spike, the thing that's putting a lot of mass close to 0, instead of being a point mass at 0, is a normal distribution itself. But this variance of this normal distribution is restricted to be less than the variance of the slab, and therefore it's more focused around 0. And you want this variance to be small so that you still have something that effectively is like a spike at 0, but it's sort of a continuous approximation of that. Okay, and this has some nice features. It leads to very straightforward updates of these gamma j variables, but it requires good choices of both of these variance components. We'll see for the prior distribution that we use that the selection of the variance component can be very important. And in this case, you would have to choose 2 of them. But nonetheless, this is another very useful prior distribution. But we're going to focus on the other one. But you can think of these as intuitively, at least, while they might have some small differences in implementation, intuitively, they're giving you very similar things. All right, so there's a reason we're using this prior distribution, or I'll call it this model, right? Is that effectively what's going to happen by introducing these latent variables gamma j, we're going to be essentially performing variable selection or model averaging, right? Because it's going to increase how many parameters are exactly 0, right? So it's going to reduce the number of non-zero parameters, as I've said here. But what you can do is, you introduce this latent variable, but that's actually going to be one of these things that we're interested in. We can look at the posterior distribution of this latent variable. So look at this quantity here to see how important a particular covariate is to an outcome. So if it has a very high posterior inclusion probability, which is what I would call this, right? It's included in the model a high percentage of the time. That means it's important, right? The data is dictating that it is important for the model, and so it's putting it into the model. It's usually included as a component of the slab. However, if this is very small, this probability, then it's more likely to be in the spike. It's not as important for predicting the outcome. Okay, and you can also you don't have to look at these things individually. You can look at the full posterior distribution of this gamma vector to try to see which models are most supported by the data. Okay. Now, another important feature is that this prior distribution, right? So it's doing this discrete thing where it's zeroing out some things completely, right? So there are, for the predictors that make it into the slab, they're still shrunk. There's still a variance of that slab distribution. There's that variance of the normal distribution, which is going to effectively shrink some of the coefficients towards 0 as well. Not exactly to 0, but shrink them a little bit towards 0. And the magnitude of that shrinkage depends on this variance component, sigma squared beta, which we're going to talk about in more detail later.
We have a
question. Yeah, there's a question in the chat here. It says, is this statement right? The magnitude of tau controls the proportion of non-zero betas. It's a very good question, and we're going to get to it a little bit more later, but yes, you are right. Right. So if you increase tau, then you are going to increase the amount of non-zero betas. Right? If you force tau all the way to the extreme, you make it 1, then everything is going to be non-zero. Right? And we'll see how this affects your posterior inference in a simulated example in 10, 15 slides or so. There's another question in the chat, was what if you make gamma j a continuous random variable between 0 and 1? I suppose you could do that. I don't know exactly what that would give you. I'd have to think a little bit harder about that. Although it's not something that I've seen done in this literature of spike and slab prior distributions, it might be a useful thing to do, but I'm not exactly sure how you would implement that or exactly functionally how that would work.
It should have some relationship to the continuous shrinkage priors, and we have some references at the end relating to those. Yeah.
Yeah, that's a great point. Actually, I think that you're spot on with that. Okay, awesome. Thank you for the question. So we'll keep moving on then. And we'll probably take a break here in 45 minutes or so. We'll take about a 5-minute break, but hopefully everyone's still going strong. All right, so what we'll see is that, and you're sort of hinted at that with these questions that were just asked, is that the performance of these prior distributions, how well they actually identify the non-zero predictors, the important predictors in the model, depends heavily on how you choose the hyperpriors, right? So how do you choose tau, right? How do you choose sigma squared beta, the variance of the slab component, right? How you choose these, whether how you update them, whether you fix them, can really impact the performance of your model. And it can take you from these being very useful, very good models to use to being basic, to being ones that are doing really poorly, right? So it's very important that you get these right, you get these spot on. All right, so tau here represents the prior probability that a coefficient is non-zero, right? So in some sense, as was hinted at with the question, is it's kind of telling you about the underlying sparsity in the model, right? If tau is bigger, we believe that there's less sparsity in the model. We believe there's more non-zero coefficients, whereas if tau is really close to zero, then we believe that there's more sparsity. And what I mean by that is that there are more zero coefficients, so less non-zero coefficients and less important coefficients in the model, right? So the variance, though, so I think tau is a bit intuitive, right? Tau is directly linked to whether something gets included in the model or not. Variance component, sigma squared beta, also has a big impact on coefficient estimates, right? So as we talked about previously, it affects the amount of shrinkage of the coefficients that are deemed important. They still get shrunk towards zero to some degree, and this controls how much those things are shrunk. And shrinkage can be a very good thing in many cases, if it's done properly. But also, we'll see is that it affects variable selection properties as well, which I think is less intuitive, at least to me. When I first started using these, that did not immediately jump out at me as something that I would have to worry about. I really kind of thought about tau as the parameter that dictates the posterior inclusion probabilities. But sigma squared beta, we'll see, also has a big effect on that as well. Okay, so in terms of updating parameters, now we're going to spend a few slides on that.
We do have one more question from the audience, asking, in fact, are we talking about mixtures of Gaussians, I assume for the beta coefficients?
Yeah, so we're not going to be talking about a mixture of Gaussians, but that is a possibility. So the prior distribution that we showed on, so our prior is a mixture between a Gaussian, one Gaussian, and a point mass at zero. But this other one, which I've shown on this slide, right, the one in the George McCulloch in 1993, which is also commonly used, is a mixture of two Gaussian distributions, right? And so that is, and so this whole idea, this framework of spike and slab prior distributions can absolutely be applied to a mixture of Gaussians, and this is how one might do it. But generally speaking, for the rest of it, we're going to be doing the point mass mixture and the Gaussian. Okay. All right, so now let's talk a little bit about the updates of these parameters, right? So we'll talk more about how to update tau and sigma squared so that you get good performance in a second. All right, there's one more question, but Tony, do you think you could address that? It looks like more looking for some references or something.
Yeah, I'll take a stab at it, although it's a little not entirely sure what's being asked. I think a topic list.
Okay, sounds good. So, all right, so in terms of updating model parameters, so we have the most important things that I'm going to spend the most time talking about are how you update beta j and gamma j, right? These guys are the most difficult things to update first, and they're also the most important for what we're talking about today, right? Which is how to, we're focusing on these spike and slab prior distributions, which are directly affecting beta j and gamma j. Right? So one might think, well, let me just apply a Gibbs sampler, right? That's the first thing that I think of, right? I'm not an MCMC sampling expert, but that's the first thing that I would think to do in that setting, right? So I could update from, consecutively update from the full conditional distribution for beta j given the remaining, right? So when I put this dot here, I just mean given everything else, right? So this is the full conditional distribution. So given all the other parameters and the data. right? And so I could update from the one for beta j, then for gamma j. I could repeat this for all p covariates, right? And then I could also update these two hyperpriors, right? I could update tau, I could update sigma squared beta, and I could just roll through it, right? Just like a traditional Gibbs sampler. And this would seem to be very straightforward. Unfortunately, it doesn't work out that well. And the reason for that is the conditional update of gamma j, right? So let's look at that in particular. We're going to spend a lot of time talking about how to update the conditional distribution for gamma j, right? So I've written it out more explicitly here. So this is the distribution of gamma j, so the probability that's equal to 1, given all of the other parameters. So the important thing here is that it's also given beta j, right? So keep in mind, intuitively, gamma j is a latent variable that indicates whether beta j is non-zero or not. But we're conditioning on beta j in this probability, right? So whenever I write negative j, I'm just letting that to be the vector of regression coefficients excluding the jth one. Same with this gamma as well. What we see is that this probability is just either 0 or 1. It's just an indicator of whether beta j is equal to 0 or not, right? But this makes sense, right? Because gamma j is a latent variable indicating whether beta j is 0 or not. And so if we condition on beta j, we know what beta j is. So if we know that beta j is not 0, we know that gamma j should be 1. And alternatively, if beta j is 0, then we know that gamma j should also be 0, right? But this isn't interesting to us. We're not going to be able, we're going to get stuck here, and we're never going to be able to explore the space of possible gamma vectors. It'll never change from your starting values, because what will happen is you'll update from gamma j given beta j. If beta j is non-zero, then gamma j is 1. And then when you go to update beta j, well, given that gamma j is 1, you update it from a continuous distribution. It's non-zero. And you continue in this cycle, and things never change, right? So you're never actually exploring the model space. You just, whatever you start your algorithm at in terms of the gamma j's is where it will finish, and it will never explore anything, right? Which is obviously not ideal, not what we're interested in. Okay, looks like there's a lot of questions in the chat. Oh, it looks like you're criticizing it. Thank you, Tony. So moving on, the main way to avoid this issue is to integrate out the regression coefficients when you're updating gamma j, right? So we can't condition on beta j when we update gamma j, right? So here's there's a couple different strategies, and we're going to go into a lot of detail for one of these strategies. So the first one, a strategy that people have commonly used, is to say, you know what, take this. I'm going to integrate out all the unknown parameters, and I'm going to update from the posterior distribution of gamma given the data, right? So I'm not conditioning on any other than parameters here. And the way you can do this, right? So if I just apply Bayes' rule to this expression, then I get the likelihood of the data in the parameter vector gamma. You have a prior for gamma, and then you have the likelihood of the data, which is integrated over this gamma vector. Okay. So this is a perfectly valid strategy, and one that's very useful, and will explore the space of possible gammas very well. Right. So essentially what you do here in this strategy is you follow a sequential updating strategy where you first update from gamma given the data. Right. So you essentially learn what the model is. So you get a sample of what the model should be, which covariates are included in the model. And then given that, you update from the remaining parameters. But updating from the remaining parameters given the model is very easy. Right? If you've ever coded up an MCMC for a linear regression, where you're not doing any sort of model averaging or variable selection, right? Those updates will look identical to the updates here, right? Because essentially, when you pick a linear regression model to start with, you're essentially picking the model. So this is the same thing as conditioning on this model. Updating these parameters is straightforward. And so as long as you can do this, as long as you can update from gamma given the data, then you are set and you're off and running. Okay, but there's one issue with this, which in some cases is not an issue, but it is one possible stumbling block, is that you need to know the marginal likelihood of the data. Right? You need to know what the likelihood of the data is given gamma, right? Now, this is not always straightforward to calculate. Right? So there are certain settings when this expression is analytically tractable. Right? So there's a nice closed form expression that you can write down for this likelihood given gamma. So linear regression, the setting that we're considering today, is one of those scenarios. Right? So we could absolutely do this for linear regression. But it's somewhat computationally heavy. Right? Calculating that expression is somewhat difficult as the sample size grows. In other settings as well, right, this does not necessarily have a closed form expression. Right? And in some of those cases, you can use approximations to try and approximate that likelihood. So there's a BIC approximation is one commonly used one. But these have some flaws and they're not perfect and they're not sampling from exactly the distribution you want. They're sampling from an approximation of it. Right? And I want to reiterate that even if you did know the marginal likelihood, it can be sometimes very computationally heavy to calculate and therefore to implement. So we're going to take a slightly different approach today, but this one is very useful and very valid as well. And you might see this one in the literature used. We're going to take a somewhat different choice, which we're going to see is really, really easy to calculate, which is why I wanted to go through it in today's lecture. We're going to be able to go through it in explicit detail. We're going to be able to show you the steps for how to do it. And I think it will really illuminate how, at least for me, when I first started using these prior distributions, I didn't know how to sample from these models. And I would read papers that would have their different way of sampling from these parameters. And it took me a while to kind of figure it out. And it was kind of daunting. And I think you'll see if you do it this way, it can actually be quite straightforward. And so we're going to walk through that here. Okay, so what we're going to do instead is we're going to modify our Gibbs sampler a little bit. Right? These steps are all going to be the same, how you update all the other parameters. But the way that we update beta j and gamma j is going to be a little bit different. So we're going to do them jointly, essentially. Okay, and so what we're going to see is different from that basic Gibbs sampler, which we know doesn't work. We talked about why it doesn't work and why you'll never move and explore the model space. And we're going to see how that if we sample beta j and gamma j correctly together, that it's going to be very easy computationally. It doesn't have the problem that the previous approach did, where you get stuck at a particular gamma j value, right? And so I think it's very fruitful. And what's even more nice about it is that computationally, it's not heavy whatsoever, right? So what I'm saying by that is, and we'll see with this when we do the R code, is that, so in the R code, we're going to look at a case where we have 100 samples and 100 covariates, and we're going to be able to sample from that MCMC very quickly, okay? All right, so what we're going to do to sample successively, or to sample this vector, these two parameters, beta j and gamma j, from their full conditional distribution, we're going to successively sample from two things. We're first going to sample a gamma j, and then given gamma j, so conditioning on gamma j, we're going to sample from beta j. Okay? So notice in this first expression here that we're not conditioning on beta j. Okay? We're integrating out beta j, so it's not part of this full conditional distribution, right? Because we saw that if you do condition on it, it's useless and we'll never explore the model space. So we're going to get rid of beta j here, and then conditional on our update of gamma j, we can update beta j. Okay. Now the second of these two things, beta j, we're not going to spend a lot of time talking about. I have the code to do it, and we'll go over that shortly. But this is a very straightforward update. So this would be a standard linear regression update. If you want to update one parameter from a linear regression, its full conditional distribution has a really nice, simple, normal distribution. Right? It looks a lot like your standard normal updates. If you have a normal prior and normal likelihood, you get a normal posterior. It looks much like that. The part that we're going to spend time talking about is this guy. This is the new thing, right? How to update this variable inclusion parameter, gamma j. Okay. All right, so how do we go about doing this, right? This is not immediately obvious to me. So how do we go about updating from this gamma j? I said that we're going to integrate out beta j, but what does that mean? How exactly do you implement that? How do you go about doing that? What it turns out is that a clever trick, and this is not saying that I'm clever. I got this, seen from reading papers that did the same trick, and then that's how I ultimately implemented these methods myself, is a simple little probability trick. Makes this extremely easy to calculate, surprisingly so. Okay. And so while this doesn't look straightforward and it doesn't look like our standard thing that we were using, there's a very, very simple way to update, to calculate this probability, and therefore update gamma j. So for simplicity's sake of notation, I'm just going to let all parameters except for those corresponding to covariate j. So everything except for beta j and gamma j, I'm going to denote with theta. Right, so theta is just this big vector that includes tau, sigma squared beta, and all the other betas and gammas. it's everything except for beta j and gamma j. Okay. So what we're interested in updating or learning is this probability here. The probability that gamma j equals 1 given the data and all the other parameters except for beta j and gamma j. Right? So it turns out that one way to make this really easy is to rewrite this expression as follows over here on the right. And so this seems like it just sort of came out of nowhere, right? I just introduced that beta j equals 0. Well, first, let's talk about why this is true. Well, to see why this is true, I think the easiest way to see it is just to see that this quantity on the denominator, if you multiply it by this one here, it's essentially multiplying, you'll get the joint distribution of beta j equals 0 and gamma j equals 1, right? The joint probability. Okay, so it's essentially multiplying a marginal times a conditional to get here the joint probability. Okay, but so it might be unclear why are we doing this, right? So why have I introduced this beta j equals 0? But what we're going to see is that I'm gonna do some calculations with this right side, and it's going to be very easy to manipulate and get to an expression that is very easy to calculate both computationally and algebraically. Okay. So let's see how we can write this in terms of things that are very easy to calculate. Okay, so on the left here, so I'm going to walk through all this stuff. This is the most math. I can't speak. I don't think Tony has any more math in this, but this is the most math that I think will be in the entire short course, definitely in my slides. Okay, but I'm going to walk through each step of the way. So this is the thing on the left is the expression we had on the previous slide. This is what we're interested in calculating, right? But it's not clear how you calculate either this numerator or this denominator. So we're going to talk about now how you do that. So the first thing I'm going to do is take this quantity in the numerator and I'm going to apply Bayes' rule to it. Right, so I'm going to flip the conditioning statement. So now I'm going to get theta and data given beta j and gamma j. I'm left with then over here applying Bayes' rule. I get the prior probability of beta j and gamma j, and I also get the marginal probability of theta and the data. Okay, so I just applied Bayes' rule to this numerator. Right, that's all I did. I didn't do anything with the denominator. It's still sitting down here. So the first equality is just applying Bayes' rule. And the clever trick is really in the second step, right? So in the second step, you see here in this step is that I'm conditioning on both beta j equals 0 and gamma j equals 1. But once I know beta j, it doesn't matter what gamma j is, right? Gamma j is this latent variable indicating whether beta j is important or not. But if beta j is 0, gamma j doesn't tell me anything more about the data, right? So I can drop the conditioning on gamma j because I learn nothing. It doesn't change anything once I know beta j. So once I condition on beta j, gamma j is independent of all those other things. Right? So that's the only difference from the first equality to the second equality. Everything else, these terms stay the same. I've only changed this one on the top left, and I've gotten rid of that conditioning on gamma j for the reasons I just stated. Okay, and then lastly, this third step is also, so we're going to see is that now I'm using the proportional to symbol. What I'm able to do is I'm able to drop this term and this term, right? I don't know how to calculate these. I don't know how to calculate P of theta and the data, but I can drop it. The reason for that is because it has nothing to do with gamma j. Whether gamma j is equal to 1 or gamma j is equal to 0, this quantity is the same. It's just a constant with respect to gamma j. And so is this, now that we've dropped gamma j from this expression. So we can drop those two out. We can say this is proportional to just these two quantities here. Okay. So just to recap, the second equality held because this should say equality, not quality, because the gamma j, once you know beta j, gamma j doesn't tell you anything about the likelihood. And then the third step is just because these guys are not functions of gamma j. They're constants with respect to gamma j. Okay. So we're almost there. So now this looks a little bit easier to deal with, but let's actually write it down what it is. So first, the numerator looks very simple because it's just a prior probability. So that should be very easy to calculate. We know what our prior distributions are. We should be able to calculate this. So I can rewrite this as, in terms of its conditional times its marginal. So I can say that this is equal to the probability that beta j equals 0 given gamma j equals 1 times the probability that gamma j equals 1. Okay. I'm not going to change the denominator at all. I'm going to leave it the same. All right, so let's look at these things now. Each of these three components. Can we calculate each of these three components? Well, first, the probability that gamma j equals 1, this is the prior probability that gamma j equals 1. We're not conditioning on data here. So that's very easy. That's just tau, right? That's that parameter tau that we had, the mixing proportion of our spike and slab prior distribution. All right, so you get tau here. So that part's very easy. This other part in the numerator is quite straightforward as well. So given that gamma j equals 1, so given that that means that beta j is going to be from the slab component of the prior, which means beta j has a normal distribution centered at 0 with variance sigma squared beta. So here, this probability is just the density of a normal distribution evaluated at 0. Right, we're trying to evaluate it at 0 with mean 0 and variance sigma squared beta. So it's just a normal density, which is very easy to calculate. Now, the last step is to see is that this here is actually just the conditional update of beta j given everything else. Right, so what is the distribution? I said that it was easy. We go back here. I said it was very easy to update from this conditional distribution. But that's all this thing is here. It's the full conditional distribution of beta j given everything else. And it turns out in this case that it's just a normal distribution as well, except the mean and variance are now dictated by both the prior distribution and the data, because this is a posterior, right? This is not a prior distribution, this is a posterior distribution, right? And so it's a normal distribution that density evaluated at 0 with some mean and some variance, right? But these mean and variance are easy to calculate. These are the standard updates for a mean and variance to update a linear regression parameter. And so this is extremely easy to calculate. We don't have to calculate the marginal likelihood of the data, right? We don't have to do anything computationally burdensome. We just have to calculate essentially this ratio of these two densities, right? Which is extremely computationally easy. The only thing you have to do is calculate m and v, right? But the thing is that you have to do that anyways. If you want to update beta j from its full conditional, you're going to have to learn or estimate, or sorry, not estimate, calculate what m and v are. And so this is not adding any computation that you didn't already have to do to update beta j. So essentially we've added no computational expenses, which is very, very useful. Okay, so what I did just now, right? So if you didn't follow all the steps of the math, that's okay. What I really wanted to get out for you is that this quantity we needed to calculate can be written as something that's very simple, very computationally easy to calculate. Both algebraically, it's very easy to see what it is, but also computationally, it doesn't add a lot of heavy matrix algebra to our MCMC algorithm. So I have now the probability that gamma j equals 1, but I only have it up to a proportionality constant. So I can't sample from it just yet. So what I can do is I can do the same thing for the probability that gamma j equals 0. I can follow the exact same steps that I did before. The exact same steps hold. And what you're left with is a ratio of these three things, just like you had previously. But it's even simpler in this case, because if gamma j is equal to 0, we know what beta j is. Right? If gamma j is equal to 0, then beta j comes from the spike, which is a point mass at 0. So here we are. That's just 1, right? It's a point mass at 1. It has probability 1 of being 0. So this is 1 in the numerator. This is 1 in the denominator. The prior probability that gamma j equals 0 is simply 1 minus tau. Okay, so there's a couple questions here that are sort of indicating I'm being a little bit loose with my notation here, kind of bouncing between probabilities and densities, but these are just densities, right? So these are going to be densities of beta j evaluated at 0 with some mean and some variance. Does that make sense to everyone? So it's just a probability density evaluation. Okay, so feel free to jump in the chat if that doesn't answer the question adequately. Okay, so to finish this thought up, right? We can do the following. There's another question, which is in the Q&A, which is if the evaluation of phi is really easy in high dimensions, but phi is a univariate normal distribution. right? So the fact that we're in high dimensions doesn't change anything, right? So we're just doing things one covariate at a time, right? So that's just a univariate normal. You're going to have to do it many times, right? So you're going to have to do it p times. So that is going to increase your computational burden to some degree. But individually calculating these fees is not terribly difficult. Okay, so let's move on. All right, so the last thing we need to say here is this. These are both proportional to these things. The probability that gamma j is equal to 0, given the data and the remaining parameters theta, is proportional to 1 minus tau. For the other one, we had that it was proportional to this, right? So all we have to do is make them sum to 1, right? Right now, these probabilities don't necessarily sum to 1, and they must sum to 1, right? And so what we can do is we can just normalize them by their sum. So if I want to sample gamma j, I just update it from a Bernoulli distribution with probability given by this expression divided by the sum of the two expressions that we found. Okay, so this is extremely easy to calculate. There's no difficult matrix algebra to be done, right? So the only real computation is you have to find these m and v quantities, right? And it turns out that, again, we already have to do this, right? When you update beta j, you have to calculate these two quantities anyway, right? And so you're not adding any computational burden on yourselves, okay? The main thing that this relied on, and when you can use this type of trick, is that you needed to have a closed form update for this conditional distribution of beta j given the rest, okay? So in our case, that works out. For linear regression, it does. You have a normal distribution for this full conditional. For other models, for like generalized linear models, for instance, if you do things in a certain way, if you use latent variables to update your MCMC, you have the same exact thing. So this expression will hold very well for generalized linear models as well. And I've also seen this used in other manuscripts in other settings as well. Okay, so this, generally speaking, the fact that you have a closed form update for this quantity is going to be very commonly true. And then you can apply these methods. Okay. Now we can think about this expression a little bit to think about whether this is intuitive or not. So let's just focus on this one here, right? This is related to the probability that gamma j equals 1, right? So if this quantity is bigger, it's more likely that gamma j is equal to 1. So let's think about what this is. So the numerator is just some prior, right? The data doesn't affect this in any way. The denominator is what affects this quantity. Right? So of course, if a particular coefficient is very important, it's very far from 0, we want gamma j equals to 1. So we want this to be big, right? We want this probability to be high. What happens though is that if you have a very important predictor, the data is likely going to tell you that it's very far from 0, its true coefficient value, and therefore it's extremely unlikely the density at 0 will be very small. The data will be strongly suggestive that 0 is not a likely value, right? And so this density will get very small, making this overall quantity get much larger, right? Which is what we want. Alternatively, if the data does not support that, if the data centers the regression coefficient around 0, right, then this density will be much larger, making this quantity get smaller, and therefore you're more likely to leave that coefficient out of the model entirely. Okay. All right, so let's move on now. Let's see how we're doing this yet. Okay, looks like Tony has it covered. So let's move on. All right, so basically now we've done the hard part in terms of updating the gamma vector, right? Updating the variable inclusions is sort of the hard part of any MCMC with respect to this model averaging stuff. Okay? Updating the remaining parameters ends up being relatively straightforward. Okay, so the remaining parameters, tau and sigma squared beta, well, as I said earlier, they're very important, and we're going to see why that is in a second. That results can be very sensitive to their choice. So one way to update these parameters is just to assign hyperprior distributions to both of these and let the data update them. Let the data inform what their values should be. Okay? These are relatively straightforward to implement. There are conjugate priors that are commonly used for both of these parameters. Right? And so this is one strategy that we could take and one that we're going to take today. So for the tau variable, so remember tau is a probability. right? It represents the prior probability that a given predictor is in the spike or the slab component of the prior distribution, right? Or the mixing proportion of the spike and slab prior distribution. We can assign a beta prior distribution to that. And we'll see that this is going to lead to a conjugate update so that the conditional distribution of tau, given the data, will just be a beta distribution as well. And it'll be very easy to sample from. One choice that is typically used in high dimensional settings is to let this prior distribution depend in some way on the dimension of the problem that you're facing or the number of covariates that you have, right? So tau here is we're assuming that tau follows the beta. So this B here denotes a beta distribution with some constant C as its first parameter and P, the dimension of the problem, as your second parameter. Okay? So C is some pre-specified constant. Its results should not be too sensitive to this, but typically it's set to something relatively small, like 1, 2, 3, whatever. But why people do it this way, why they let the second parameter of the beta distribution be P, which is the number of covariates, is that the mean of this distribution ends up being, if you remember back to your probability class, what the mean of a beta distribution is, it ends up just being C over C plus P. And what this means is that if you have more covariates, the mean of this distribution is going to be closer to 0, right? The idea being is that as you have more and more covariates, right, a priori, we're not going to let the number of things that we include in the model grow just because you're including more features, right? It stays relatively constant. And so the percentage of sparsity or the percentage of variables that are non-zero decreases. I think that a really nice paper, which I think we also point to at the end of the slides, is this James Scott and Jim Berger paper from 2010. It's a really great paper on sort of the implications of the different ways of updating tau, for instance, and the impact that this can have on the variable selection properties of these models. So I would point you guys to that, and the reference should be at the end of the slides if you're interested in reading a paper more about that. But here's just a simulated example, just to sort of illustrate empirically the impact that tau can have on the results in these models and the importance of this tau parameter, right? So here I've made 4 plots here, analyzing the same data set. So here, the light blue dots are those that truly have an impact on the outcome. So this is simulated data, so I know which ones actually are associated with the outcome, right? And so we want the light blue dots to be very close to 1, exactly equal to 1 if possible, because on the y-axis, we're plotting the posterior inclusion probability. So this is the probability that gamma j equals 1, given the data. For the important covariates, you want it to be very close to 1. And for the darker bullet points here, we want them to be very close to 0, right? And so if I just fix tau, so I fixed it at a few different values here. I fixed tau at 0.01, which enforces a lot of sparsity, right? That's really enforcing that very few things make it into the model, right? Then we see that, okay, the important predictors are mostly getting into the model, but one of them is only making it in 70% of the time, whereas the non-important coefficients given by the black dots are all very close to 0. That part is good. If we increase tau, so we increase it to 0.25 or 0.5, then the light blue dots shoot up to 1. So they're all 1, which is what we want. We want them to be included in the model all the time. But we start getting something like false discoveries, right? We're getting these black dots, which don't have any association with the outcome, and these should be close to 0. We're starting to get posterior inclusion probabilities for those covariates that are too high, right? So as I increase tau, they get larger and larger. And if tau was 0.5, right, then you see that they're just all over the place. Okay. Now, if I put a hyperprior on tau, so I use that beta prior distribution I talked about on the last slide, then what I get over here on the right is, bottom right, is very good performance. The blue dots are almost all equal to 1, the exception of that 1, but it's much higher than if we had set tau equals to 0.01. It's about 0.9 or maybe slightly higher. But most of the black dots, the irrelevant covariates, are also very small. Right? We get a couple of them that are popping out around 0.1 or 0.2, but for the most part, they're all very, very close to 0. Right? So this is good. So it seems like the fully Bayesian approach, which assigns a prior distribution to tau and updates it as we go, does pretty well at finding a good balance between power, sort of finding the important predictors and excluding the irrelevant ones. Okay. So in terms of tau, I think it's somewhat intuitive. That's the more intuitive of the nuisance, or not nuisance parameters, of the additional parameters. It's more intuitive that that one affects variable selection performance, right? It's the prior probability of inclusion for each covariate, but of course, if we increase the prior probability of something, the posterior probability is going to shoot up too, right? And the degree in which the posterior goes up with it depends on how much data you have and so forth, right? But increasing tau is going to increase your posterior inclusion probabilities as well, right? I think that's fairly intuitive, right? Given what we know what tau is. The variance component, sigma squared beta, on the other hand, is a little bit different. It is not as obvious how sigma squared beta affects inference in these models. Now, we already briefly talked about sigma squared beta, right? And what use it can have. And so it is the variance of the slab component of the prior distribution, right? And so any coefficients that make it into the slab that have gamma j equals 1, right? Those are going to be shrunk somewhat towards 0. Even though they're going to be non-zero, they're going to be pulled somewhat towards 0, right? And the degree of that is given by this variance. If there's a really big variance, then they won't be shrunk at all. If there's a very small variance, then they might be overly shrunk towards 0, right? But the shrinkage can be a good thing, right? You're going to reduce the variability of your resulting estimates, so you get this kind of ridge regression type shrinkage towards 0, which can improve prediction performance and sort of overall improve your model. But what's unclear to me is how does it affect variable selection? And does it affect variable selection, this spike and slab variance, right? Again, we know that tau does, and that's intuitive, but it's not clear if sigma squared beta will. So let's look at this term again, right? This is the term that we ended up using to update gamma j, right? So we have the density, the prior density, the beta j is at 0, right? With mean 0 and variance sigma squared beta. And then we have the posterior density, right, of beta j evaluated at 0, right? So obviously this is an increasing function of tau because tau is in the numerator only. So if you increase tau, this thing's going to go up, right? On the flip side, though, sigma squared beta shows up in both of these expressions, right? It's not just in the numerator, it's also in the denominator, okay? And so it's unclear which side wins out. If you increase this variance parameter, both the numerator and the denominator are going to change somewhat, but it's unclear which one's going to change more than the other and which direction the variable selection performance will go, or whether it'll just be kind of random, whether there's a trend or not, is something that I think is important to understand. Okay, and the reason why sigma squared beta shows up in both the numerator and the denominator, I think it's clear why it shows up in the numerator. It's the variance of this normal density, of this normal distribution. M and V, however, in the denominator normal distribution are also functions of this variance component. So it shows up in both aspects here. So here's a similar plot to what we did with tau, right? But I showed for 6 different values of sigma squared beta. So going from top left to bottom right, we're increasing the size of this variance component. Okay, and we see something very interesting here. There's not a sort of monotonistic relationship. There's kind of this interesting relationship that you can get bad results if you go in either direction. Okay, so let's look at the small case. Let's look at the top left case where sigma squared beta is really small, right? If sigma squared beta is really small, then the light blue dots, the ones on the left, we want them to be high. They're being pulled towards 0, which is bad. But at the same time, the dark black dots are being pulled up from 0 relative to what we saw on the previous slide with the tau changing, right? So we're getting bad performance in both ways. We're not just getting worse performance of the important predictors, but we're getting worse performance of the non-important predictors as well, right? So this is just horrible. This is just not good in overall. This is had a negative impact on all aspects of variable selection, both reduced our power and increased our false discovery somehow, right? But the reason for this is that if you set that variance component to be too small, and how small is too small depends on the problem, you know, your residual variance in your data, et cetera. But in this case, 0.01 seems to be too small. And what happens is if you set this variance to be too small, one, you overly shrink coefficients towards 0 that make it into the slab. But I think a bigger problem, which is evidenced here, is that you cannot distinguish between the spike and the slab if the slab variance is too small. Right? The spike is a point mass at 0, right? The slab is supposed to be this diffuse distribution centered around 0. But if you make the variance too small, it starts to center around 0 as well, right? So at some point, if you make the variance really small, the slab distribution looks a lot like the spike. It's sort of a continuous version of the spike, right? Yes, technically it assigns density everywhere, but most of that mass is right around 0. And therefore, the data doesn't know whether something should be included in the spike or the slab, whether gamma j should be 1 or 0. It doesn't know because essentially the spike and the slab look the same, right? So that's not ideal. So you need to make the variance a little bit bigger than that, so that doesn't happen. And we see that as soon as we make the variance bigger, so in this case, we get it up to 0.1, the blue dots, the light blue ones, which we want to be close to 1, shoot up toward 1, which is good. And the black dots here are much lower, or lower than they were for 0.01, okay? And what we see, okay, so that's one interesting problem that it can occur with the slab variance. Another problem is that if you make the variance too big. So as we go from top left to the bottom right now, we see that, all right, so we make, the variance goes to sigma squared equals 1. That seems to be working reasonably well. All the light blue coefficients are close to 1. The black coefficients are close to 0. That's great. For sigma squared beta equals 5, we're still doing pretty well. But then as we get bigger and bigger, everything is being excluded. So the black dots are almost exactly 0, which is fine. That's a good thing for us. But the light blue dots are starting to be pulled away from 1. They're starting to be excluded from the model even when they shouldn't be. And if you go to some extreme here, you set a very wide variance, then you get almost nothing is included, even the very important ones, right? 3 of the light blue dots have posterior inclusion probabilities equal to 0. One of them is hovering around 0.4. If I were to make this variance even bigger, it would probably go all the way to 0. Okay. And so this shows you that you can't just assign a diffuse prior to the slab. You might think that would make sense. You say, normally when I do linear regression, I put a diffuse prior distribution on my variance components, right? And so why can't I do that here? I let the spike and slab figure out which ones are important, but for the important ones, I want a diffuse prior. Well, it turns out you can't exactly do that, because if you make it too big, right, then the inclusion probabilities shoot downwards. Okay, so there's a question in open question in the chat, but Sam, if you could read, I'm not sure exactly what your question is. So if you want to.
The question was, I think you had said something about it, as sigma small, it's centering around 0. The question was just asking, aren't they all centered around 0? And I said that I think you meant concentrate around 0.
Sorry, I apologize. Yes, they're all centered at 0. They're all middle of the normal distribution of the slab is always 0, but it'll be more and more concentrated at 0 as this variance gets smaller. My apologies. All right, so hopefully that is intuitive now, that you can't just submit a diffuse prior distribution for the variance components, and you'll get poor performance in terms of the variable selection. You're going to be excluding things that are actually important. All right, so you need to find a variance sigma squared beta that's somewhere in the middle. Okay, so we can place, by the way, we're going to take a break in just a couple of minutes here. So I'll get through, if there's any questions in the chat, we can deal with them in a second. We're going to break in about 1 slide. So we'll take care of any remaining questions there while we take a break. So the last thing is we have to update this sigma squared beta, right? So what we can do here is you can place a conjugate prior on sigma squared beta, right? So you could put an inverse gamma prior distribution on this variance component, right? That's one way to do things. Another thing that I've seen is that you could specify down here a separate slab variance for each individual regression coefficient. So each one, which I'm denoting now with sigma squared beta sub j, has their own unique slab variance, and you put separate inverse gamma prior distributions on all of those, right? Now this has some pros and cons to it relative to the one above, which is a variance component that is shared among all the covariates, right? You have less data to update these parameters because you're only using one covariate for each of these parameters. So they tend to be more variable. But what it can do, which is very useful, is, and it highlights an issue with the approach above, using the same one for all coefficients, is that if some coefficients are really large and some are much smaller, what you might end up having if you have one variance component for all of them is that you're going to end up with kind of something in the middle, and you're going to overly shrink that really big coefficient towards 0, right? And so having a separate slab variance for each coefficient allows for, if a coefficient is really large, right, you can reduce the shrinkage of it towards 0 by letting it have its own variance component, which can be larger. Okay. Lastly, both of these parameters, so we took a fully Bayesian approach to updating these parameters already, but they can both be estimated using an empirical Bayes framework as well. Okay. Right, so you can estimate these things using empirical Bayes before you run your MCMC, and then condition on those estimates and leave them fixed throughout your MCMC. That also tends to work well. We focus on the fully Bayes solution here, but there are ways to do it this way as well using empirical Bayes, and we could point you to some references if you were interested in pursuing that strategy. So now we're going to take a break, because we're going to look, next thing we're going to do is look at some R code to see how MCMC for this very simple model works. So these ideas that I showed you on these slides here, we're going to discuss these in the context of R code briefly, and then I'll finish my portion before Tony gets started. So let's take a 5-minute break, and then we'll come back and get to it. And in the meantime, I'll see if there's any chats that need to be addressed. I think Tony's probably addressing them, but I'm happy to talk now.
There was some question in here. I haven't responded to it yet about I think just the intuition behind what the role of sigma beta is, or why you get this kind of why taking it too big actually kills things. Because I think people have this intuition that maybe they want to have, they're used to setting these variance parameters as being very large, with the idea that they're kind of uninformative. And it sort of doesn't work for variable selection problems, which is a pretty well-known phenomenon. And I mean, mathematically, you can kind of understand it just if you look at that ratio that that Joey had of the tau. What was it? The we have like a tau times a phi divided by another tau. You can read off directly from there that if you send sigma squared beta, I mean, I guess it's not obvious because there's stuff hiding in the v, but the numerator will go to 0 because that's a normal density. As you make it flatter and flatter, that term goes to 0, and it turns out that the v does the variance of the numerator goes to infinity, meaning that that term goes to 0. But the denominator actually stabilizes. So analytically, you can see that all of the probabilities will be going to 0. Intuitively, it kind of makes sense as well, because you're sort of forced to choose between, if sigma squared beta is too big, there's two ways that things can be weird, right? That something unlikely happens. Either you observed really weird data, and like either the coefficient is actually 0 and you saw something weird, like your estimated, think in terms of a beta hat, that m there. If that thing is big, then either the coefficient is 0 and you saw something weird, but if sigma squared beta is too big, then you're also seeing something weird because you expect that beta to be really, really, really big. So if my variance or my standard deviation of the coefficient is 1 billion, and I estimate a beta hat of 5, it's actually weirder that that my coefficient isn't massive. So like there's kind of this weird interplay between these things, and so that's kind of why if you make the sigma squared beta too big, you'll zero it out. Although you have to make it really, really massive before you get into extreme trouble. And now there's a bunch of questions that I guess we should probably start working through.
There's a few here. I'll go to the Q&A first and see.
There is another one in here that I meant to also mention. A lot of the sigma squared beta is related to the choice of the normal slab distribution plays a big role in these sorts of issues. if you use, say, so an alternative approach to resolving these is if you said use a Cauchy distribution, or I see this paper from Gelman being referenced. An alternate way to deal with this issue is to take sigma squared beta to be kind of middling and use a heavy tail prior, so something like a Cauchy. That's an alternate
somebody
way
hinted at that. I think Dan Phillips had a question about that, and I think he was hinting at that in the Q&A, it looks like.
Yeah, so Cauchys are often, I think even back in when a lot of these methods were being initially proposed by like Zellner and, you know, all the ancient stuff, they jumped kind of straight to Cauchys because of this type of, well, this issue and the Lindley paradox. There's some reasons for not liking the normal. But I mean, this approach works pretty well as long as you don't go too crazy with the sigma squared beta, or you do something reasonable. Maybe put a prior on it or something. You can also do.
So here, Eduardo has a question about the advantage of the separate slab variance strategy to updating sigma squared beta. Can I briefly go over it again? And I think this kind of hints at some of the stuff that Tony was just talking about too, and other ways to avoid this over shrinkage, right? But what I was saying was that if you have a separate slab variance for each coefficient, then if you have a coefficient that is really large, then it can have a larger slab variance that won't pull it towards zero as much, right? Whereas if you have one central slab variance that is sort of a one size fits all for all the covariates, it may be too small for that one coefficient. It might work well for the other ones, but it'll pull this one coefficient too far towards zero. Whereas if you allow them to have separate variances, then that doesn't necessarily happen. But as Tony was saying, there are other ways to address this problem of overly shrinking, using prior distributions other than the normal distribution for the slab, et cetera. There are other ways to avoid this issue. We're just sort of sticking to the basic spike and slab with the normal distribution here. Okay, there's lots of questions. These are great. One question about, would it be a problem if we updated beta with a multivariate normal distribution instead of updating them with a univariate normal? No, that would not be problematic. You could update groups of parameters together if you wanted to, and then the betas would follow a multivariate normal distribution, and you could follow a similar strategy to doing that. Also, we're going to see later on in the lecture after the R code that we're going to actually do things with a multivariate normal distribution for the nonlinear setting as well. Danielle has a question about what are the advantages of performing variable selection instead of simply applying shrinkage and then inspecting the magnitude of the estimated parameters. I mean, I think that's a totally valid way to do it too. What's nice about this is that it gives you something that's interpretable more so than anything. You look at these, you can look at these gamma J's, which kind of gives you a more formal assessment of whether something is important or not. Whereas in the shrinkage setting, you're going to get varying magnitudes of the absolute of the coefficients, right? And you'd have to somehow try and find a cutoff for what is deeming something important or not, which you could do. I think I have seen that done before, where you try to find, you would say kind of above, if a coefficient has a posterior mean above some threshold, then you would deem it important. But I think people like these gammas for their interpretation, but you could do something like that as well, which is more of like a post hoc strategy to identifying which things are important. The last question includes something with the Savage-Dickey density ratio. I don't know what that is. Tony, do you know what that is?
I'm not entirely. Yeah, I mean, I've definitely seen that before. I don't know that I would be able to pick it out of a police lineup or anything. It is true though that, I mean, all these various paradoxes. So Lindley's paradox, that kind of is. They're all kind of related to these issues of the betas. Well, I think Lindley's paradox is what if your test statistic doesn't if your test statistic increases, then you don't necessarily get a posterior probability going to 1, a posterior inclusion probability going to 1. Which I think that one is tied up more so with the error variance as opposed to the variance of the slab distribution, I think. but they're all kind of pointing at the same thing, which is that you have to be quite careful with what you do with the variance parameters in these models. I think they're pointing to the specific, maybe the specific density ratio that you have has a particular name.
Yeah, I see that I know that's in my slides. I just don't know this paradox personally. Sorry. Okay, let's. Okay, so I think we'll get started now. I think it's been more than 5 minutes, but a lot of really good questions. Thank you all for participating and being interactive about this. And sorry if we didn't get to all of them. There were a lot in the chat. So with that being said, I'm going to briefly now go through some R code to do this. This is in the GitHub page. So if you want to look at it, I know it's hard to watch someone go over code, right? So I know this may not be, a perfect exercise for talking about this, but I thought it was useful at least a little bit to go through this code for 10-15 minutes. It's a very simple code, and just briefly go over it, how one could implement the approaches that we talked about over the last 10-15 slides or so. So again, the full conditional updates for some of these parameters, we didn't go over the explicit algebraic form for them, with the exception of the binary indicators. But I think it's still useful to go over this code and see sort of how these things are implemented in a very simple setting. So we'll do this briefly before we return back to the slides to learn about how nonlinearity can be introduced. Okay, so just as setup, we're gonna set the seed so we get the same results. I'm gonna do a situation with a sample size of 100 and 100 covariates. We're gonna just generate our covariates from a normal distribution with independent covariates with the same variance. Just the simplest setting here. And this is our true regression coefficients beta here, right? All right, so we have 4 important coefficients here, and then we have 96 that are irrelevant. And so we're hoping that our approach is able to exclude some of these approaches. Okay, and so first thing here, let's just simulate an outcome, which is a linear function of these covariates. And then we have a few things here, which are just sort of standard things at the beginning of an MCMC. So we have to keep track of how many chains we want to keep. So for this illustration, I'm just going to do 1,000 scans and 2 chains. I would recommend doing more and doing convergence checks, but we're just going to briefly go through this to see how the code works. So we're going to keep track of, we're going to go through 1,000 scans. We're going to burn the first 200 and every 4th one to get 200 samples per chain, which again is not very many, but just for the sake of speed and going through this quickly, we'll do that. All right, so for all of the other parameters other than beta j and gamma j, we have some hyperparameters that need to be chosen. Right, we have a prior distribution for the residual variance in our model, sigma squared. We have the beta prior on tau, right? So the beta prior on the variable, the proportion of the prior probability of inclusion into the spike or the slab, right? So we're going to set that constant c to be 2, and the other parameter to just be, as I said in the slides, the number of the number of covariates in our model. And then we'll have some additional hyperparameters for the slab variance that we're going to update as well. All right, so just briefly going through this again, we have to store all of our data, all of our parameters somewhere. So there's just an array for every single one of our unknown parameters that we're going to update here. So we have one for the residual variance, one for the binary inclusion parameters, one for the regression coefficients, the prior probability of inclusion, and the residual, or sorry, not the residual, but the slab variance distribution. Okay, so let's go through that. All right, and then of course we have to assign starting values for these. I'm just going to assign them some random starting values that sort of honor the bounds of these random variables. So for the variance terms, I'll just use a gamma. For the binary inclusion parameters, I just update from a binomial, or Bernoulli, I should say. the beta parameters are from a normal distribution, and so on. Okay, so let's move forward now to the actual MCMC, right? So last thing, I created this thing, which I call the design. It's just the design matrix where I appended a sequence of ones to our covariate matrix X so that we can have an intercept as well. All right, so now we're gonna update through this code. We're just gonna run a Gibbs sampler where we go through each of the unknown parameters that we have to update. So the first ones that we're gonna do, which I'm not gonna spend basically any time talking about, are the other parameters in the model. So the residual variance, the tau, and the sigma squared beta, right? These come from very standard updates. Oops, yeah, can't run that yet. We'll just run this code and then go over it. Okay, so first we update the residual variance from an inverse gamma. So we use an inverse gamma prior distribution, which leads to an inverse gamma posterior distribution. I said here that tau had a nice conjugate prior. We see that our posterior distribution that we're updating for is a beta distribution, right? With very easy to calculate hyperparameters that just are involved with how many of the coefficients are deemed important or not, or how many of the gammas are equal to 1 or 0. Same thing for the residual or the slab variance. We just update that from a gamma distribution or an inverse gamma distribution here, again, with relatively easy to update hyperparameters, right? Oh, is there a question here, Tony? Is spike and slab the state of the art? Are there other valid approaches being used? For example,
I'm working on answering it.
Okay, all right, sounds
typing
good.
it out. Yeah,
I'll let you take that. All right, and so this part is fairly standard, right? So these are type of updates that we would see if you were doing a linear regression. Sigma squared update would be the exact same as here. We have these two additional updates that are unique to this spike and slab, that are the spike and slab parameters, but they have very nice, easy to update full conditional distributions, right? This is for the meat of it, which is what we talked about for 5 to 10 slides previously, right? So before I do this, I'm going to store a temporary beta vector, right? So that I can update as I go, right? And all I'm going to do is I'm going to loop through from 1 to p. So I'm going to loop through all of the covariates in our model. And I'm going to jointly update. I'm going to update first gamma j. So I'm going to figure out whether that covariate is important or not. And then I'm going to update beta j given that gamma j, right? So to do this, the only real work I have to do is to calculate those m and v parameters that we had on the slides, right? We have to calculate what the full conditional mean and variance of beta j are. And so to do that, we need to define a couple of quantities. Here you have to define a residual. So you take the original outcomes and you subtract off the effects of all the covariates except for the one that you're interested in, right? Except for covariate j, right? You see a j plus 1 here because there's an intercept, right? But we're just removing the effect of everything except for covariate j, right? So this will be like our new outcome that we use here, right? We have some prior variance, which is just this slab variance here, right? We have our prior probabilities of being included or excluded from the model, okay? So this is just, we're going to keep everything on the log scale to make things easier. So remember on the slides, we had a ratio of 3 quantities. We're going to end up having a sum of those things on the log scale, and then we can exponentiate them afterwards. So I'm just taking the log of the probability that gamma j is equal to 0. So that's just log of 1 minus tau. So then I need to calculate that m and v quantity. So v here is this posterior variance, and m is this posterior mean. So if you've ever done a normal update, like a normal prior distribution, normal likelihood, you'll get something that looks a lot like this, right? And so this is the posterior mean and posterior variance. These are just those m and v quantities that we had to calculate. And now I can calculate that proportion, that ratio, right? So we have, first there's the tau component. So we've got log of tau, right? Then there's the numerator density, right? So the density evaluated at 0, right? This is the prior density. So it has just mean 0 and standard deviation equal to the square root of our prior variance. Again, I'm doing everything on the log scale. So I'm making everything log equals true here. And then I'm subtracting the denominator, right? Which is just, again, a univariate normal density evaluated at 0, but with mean and variance given by the posterior mean and variance, which I called m and v in the slides. Okay. So now I'm ready to go. I have everything that I calculated in those slides. There's one small issue that comes up a lot. I don't actually think it would happen if you just tried this data set that I simulated, but it comes up very frequently. And I think if I increase the sample size, it happens. Is that sometimes you get these log densities, in particular this log of P1 is too large, right? So we need to exponentiate these to get them back on probability scales, but this can be too large such that if you exponentiate it, R tells you that it's infinite, right? And then you can't update gamma j, you get an error, right? Remember, however, that these things are just proportional. They're proportional to the probabilities, right? So I can add and subtract any constant to them I want, and they're still proportional to it, the thing I want, right? So I'm just going to ensure that I don't get any errors from R running into infinity issues. That's all I'm doing here is I'm calculating the maximum of these two things, and I'm subtracting it off from these log probabilities. This is just to make sure that these numbers are small enough so that when I exponentiate them, they don't explode and R freaks out. Okay, so I get these two probabilities here. Again, these are proportional to, they're not the exact probabilities we're interested in. They do not sum up to 1, but that's okay when you use the sample function, right? You could either normalize them by doing something like calling it like P1 star, we'll say. You could just normalize them by saying P1 divided by P1 plus P0, and you could sample from a Bernoulli with that probability, right? But alternatively, the sample function here already normalizes things for you. So you can give it as a probability vector, things that don't sum to 1, and it normalizes it. So we can just put it into the sample function, and we can sample whether to include or exclude this covariate here. Okay, so now that I have an update of gamma j, I need to update beta j, the corresponding beta j. So first I'll set the corresponding beta j equals to 0, and only if the gamma j that we found was equal to 1. So only if it comes from the slab, if this covariate is deemed important, we then update this parameter vector from a normal distribution, again, with mean m and variance v, right? Which we already calculated from above, okay? And we loop through that, and this should work reasonably well. All right, so let's run it one more time. Let's just redo this whole process to see how long this takes. So to get essentially 2,000 scans, how long does it take with 100 covariates and a sample of 100? We see that it's relatively quickly, right? So even though we're in a high dimensional scenario, the computational burden of these methods is not too heavy, right? At least for the linear regression setting here. This runs relatively quickly. And as you increase the sample size or the number of covariates, it scales relatively well with those things. All right, so we can look and see what we got out. So I'm just going to keep the samples that I want. I'm going to get rid of the burn-in, and I'm going to thin them. And then I'm going to see what the posterior mean is for the gamma j's. And what we see is that all of these ones, which are not important, are all very close to 0, as we would hope. And in this case, it doesn't always work out perfectly like this, but the first 4, which were important, had non-zero beta values, all get included in the model 100% of the time. Right? They have posterior inclusion probabilities of 1. Their posterior mean of gamma j is 1. Right? We could look at their corresponding beta estimates. So for all of the non-important ones, they're very close to 0. Right? But for the ones that are important, right, so this is an intercept, so you can ignore that. The first important coefficient, the true value is 1. The next two, the true value was 0.5. And the last one was negative 0.4. So we see that it seems to be doing reasonably well, minus some sampling uncertainty. Okay, we can look at the other parameters as well, and they seem to give us reasonable values. One thing that I think is interesting is this tau parameter here, right? We've talked a lot about tau, and so we updated it in a fully Bayesian way here. And what we see is that the posterior mean of tau, it's equal to about 0.034, right? And roughly in this problem, we had 4 significant predictors out of 100, right? So roughly the true underlying percentage of important covariates was 4%, 0.04 proportion, right? And you'll see that this tau thing usually centers around that value, right? It tries to find the true underlying proportion of important predictors in the model, and that's roughly what tau centers on, or concentrates around, sorry. Okay. Okay, so there's a question in the chat about assuming there is only a single predictor, how does the spike and slab prior fitted with a single model differ from B? Oh, did you already answer that, Tony? Sorry.
No, I was just putting it in the chat so that everyone can see it, since it was only sent to us.
Oh, it was only sent to us. Okay, yeah. So assuming there's only a single predictor, how does the spike-and-slab prior fitted with a single model differ from B? Estimating two models, one with spike and another with a slab, and averaging over them with Bayes factors. Does this change when considering more than one parameter? So I will say, I think that there probably is a relationship. They're probably will give you relatively similar things if you only had one predictor. But in the case where you have more than one predictor, which is the only time that you would be interested in using these types of prior distributions, right? We would only use the spike and slab prior distribution when we have a lot of coefficients. I don't think that would work quite as well, because if you just use one model that had only the slab, right? Then you're basically saying that you have this huge number of parameters and you're just assigning a normal distribution prior to them, right? Which probably won't perform very well when P is relatively large, when you have a lot of covariates, and a lot of them aren't actually important for predicting the outcome, right? And so I think
the question is more along the lines of, whether there's a mathematical difference between, say, just doing Bayes factors, for example. And that would depend, on the prior distribution that you assign to the different models. There should be a way to write things so that they're equivalent. Like, the prior distribution on a particular model you could derive, so a particular set of gammas. So if I fix gamma, then I know that should identify a particular model, and I could compute the marginal likelihood of that model and kind of proceed through everything in terms of Bayes factors. There should be an equivalence there, I think.
But I think what you're talking about, Tony, is using Bayes factors to kind of average over the different possible gamma models, right?
Well, just saying compute posterior probabilities, so I can compute, I could compute Bayes factors, I could compute the marginal likelihood and output a posterior probability for each model. It's sort of like that expression that you wrote in terms of the gamma. Just, you wrote an expression, I think, explicitly for the posterior probability, and that should be equivalent to kind of what we've been doing, I think. There was, what else? There was another part of this question. Does this change? Oh yeah, I also, I did disagree a little bit in the sense that, I don't think you have to have a massive number of parameters to care about doing hypothesis testing.
Well, sure.
Yeah. So it's still a fair question for what you would do for one parameter.
So there's another question in the Q&A that, do you need to standardize? This is a great question, actually, and one thing that we should have absolutely talked about beforehand is whether we need to standardize the covariates before running selection using this method. And yes, absolutely. If you don't standardize the covariates, if they're on very different scales, importantly the variance of your predictors, then you can get really weird performance here. You want all of your predictors to be on the same scale before running this. So that was true in the simulation because I simulated them, but in practice, I would recommend standardizing them before you plug them into any of these models. Otherwise, you might get some very interesting results. It's the same idea of like why, if you're using like penalized likelihood approaches, you need to standardize them before running any models as well, so that the penalty has sort of a similar interpretation across different covariates. Okay, so let's move on. Okay. So let's leave the code now, and I will finish up my portion and then turn it over to Antonio's. So let me share my slides one more time. And then here we are. Okay, so let me know if you can't see these, Tony. Otherwise, I'll proceed. All right, so here we are. All right, so we finished up with the linear section. So now we've gone through some of the computational aspects of these code, implementation details, the sensitivity of these models to prior distributions, right? But we were assuming all throughout these pretty strong parametric assumptions, right? We're assuming that there's a linear relationship between all the covariates and the outcome. And additionally, we're also assuming that there's an additive relationship, right? That the effect of one covariate on the outcome does not vary by values of the other covariates. Right, so now we're going to try to work toward alleviating both of these assumptions. So I'm going to talk briefly now about alleviating the first of those two assumptions, alleviating linearity assumptions, and then Tony's going to talk about his work on alleviating both additivity and linearity assumptions. So we'll discuss two ways in which you extend these ideas to the nonlinear models, right? So essentially now we're going to write out our model as follows, right? We're still interested in the mean of y given x, right? But now it's going to be a linear function of the covariates. So it's still additive, right? There's no interactions between any covariates here, but we now have removed the linearity assumption and replaced it with some nonlinear function of x sub j. No longer assuming that this f function is linear. So at least at a very high level, what we want to do is apply the same ideas to this setup. So intuitively, that would be place a spike-and-slab prior on this function somehow, right? So we're going to talk about two different ways to do that, right? Because we either want this covariate to be removed from the model completely, i.e. in the spike, and that would mean that it's a flat function at 0, right? Or it's something important, right? Something non-zero, and then therefore has a potentially nonlinear relationship with the outcome, right? Right. All right, so we're going to talk about two ways to do this. The first is probably a little bit simpler and more in line with what we've seen previously, right? So the first of them is to make a parametric assumption about this function, but not necessarily make such strong assumptions as linearity, right? So we maybe pose some parametric model, but one that allows for a wider degree of true functions than simply a linear function. And so there are many ways to do this, but the most common way is just to use this basis function expansion. So we can assume that this function of xj, right, can be rewritten as follows, right? Is that you have these b sub k here, which are some basis functions. So we have capital K of them, right? And then some corresponding coefficients associated with them. So these basis functions can be any number of things. The simplest thing would be something like polynomials to include squared or cubic terms in there. Probably something that would probably work a little bit better might be something like natural cubic splines. You could use wavelets, anything like that, right? So there are a wide number of functions that one could use as these b sub k functions. And that's one downfall of this method is even though you don't have to assume linearity, you do have to specify what these basis functions are. So there's still decisions made on the analyst, right? A decision you make before running this. Right? But some standard choices like natural cubic splines tend to work reasonably well at capturing fairly moderate degrees of nonlinearity with only a few basis functions, okay? So you can rewrite this thing, though, as follows. You can rewrite this in matrix notation as follows. So you just have some xj tilde times beta j. So xj tilde is an n by k matrix, right? So each row corresponds to an individual, but there are k columns, one for each basis function, right? So you evaluate each of these basis functions at each of the individual data points. And then you have this vector now of regression coefficients, beta sub j, right, which is a k-dimensional vector of parameters that correspond to covariate j. Okay. So moving on. All right, so I think it's clear is that if beta j is 0, and so now we're talking about 0 being the 0 vector, meaning that every element of beta j is 0, then this entire function is 0. And that covariate no longer plays any role in the model, right? So we can do something very similar to what we did previously for the simple, more linear, in the linear case, is we can use a spike-and-slab prior distribution on this regression coefficient, beta sub j, right? So now all we have to do is extend it so that these things are multivariate instead of univariate. So now we still have a spike, which we're going to use as a point mass at 0. Now 0 is the multivariate vector of zeros here of dimension k. Right? And then here we have a multivariate normal distribution. So I've denoted that with this sub k here, dimension k, with mean being the 0 vector. So we're still centering our slab distribution at 0, but it has some variance. Right? But at least at a high level, this is the exact same thing as the simple linear case. Right? So you're basically taking a mixture between two distributions. One is essentially saying that covariate doesn't matter, i.e. they're all 0. or it does matter and all the coefficients are non-zero, right? So this is similar to other grouped variable selection approaches where you either include all of these parameters together, meaning they're all non-zero together, or they're all exactly zero together. So there are some approaches out there in the literature. I know there's a Bayesian procedure that's similar to this, which also has a second layer of variable selection where within a group that is important, you can still add sparsity to coefficients within the group. But we're just for now going to leave with this all-in, all-out structure. Okay, so either covariate is important and it's included in the slab, or it's not, it's included in the spike. But in terms of actually implementing this, there are basically no differences between this and the univariate approach that we talked about in detail, right? The one main difference conceptually is that now our slab is a covariance matrix instead of just being a singular scalar variance parameter, right? And so that seemingly could cause you problems, right? Because before, we saw that results were sensitive to choice of the slab variance, right? Which back then it was only a single parameter. Now we have this k by k matrix, right? Unfortunately, we don't want to have to update all, these parameters together, or, there's a lot of parameters to update if you let that covariance matrix be free. But typically, a couple of standard choices work reasonably well. You can make this covariance matrix be proportional to xj transpose xj inverse, right? Sort of a standard prior distribution that people use in linear regression settings, right? And just scale it by that. So now you've reduced it to a single scalar that you have to learn, which is sigma squared beta. Alternatively, you can just assume that it's the identity matrix and scale it by sigma squared beta as well. I found that both of these work reasonably well and results aren't too sensitive between the two choices. Also, always, if you have a group of predictors, you can always orthogonalize them within a group, right? And then this identity matrix makes a lot of sense. And you can always untransform the variables back to the non-orthogonal scale at the end if you need. But I think that's a little too in the weeds for now. I think it's just intuitively, we can reduce this covariance matrix to being something that we only have to choose a singular scalar parameter again, just as we did previously. Okay. All right, so let's move along. So that's fine, right? That works reasonably well, and computationally, that's extremely fast. If I were to run that code just like we did in the R a second ago, it would run at a very similar speed to the simple linear model that we had. But what if I don't want to make any parametric assumptions about this f sub j function, right? So in particular, what I mean by that is I don't want to have to specify basis functions a priori that I think will approximate whatever this true function is well. Right? Maybe the true function is something weird, and my choice of basis function isn't adequate to capture it very well, right? So it'll probably do better than just assuming linearity, but it may not do as well as we would hope that it would do. So is there anything we can do where we don't have to pre-specify this choice? We're always going to have to make some decisions, of course, but can we try to make it as easy as possible, make the fewest and least restrictive choices possible? Okay. So the non-parametric Bayesian approach would say, right, is that you would place a prior distribution on this function, right? So non-parametric Bayes as a whole kind of applies to situations where you're putting a prior on infinite dimensional spaces like this function, right? And so the easiest choice, there are multiple choices for ways to do this, but the sort of natural Bayesian non-parametric choice, or one of the most commonly used ones, is to place a Gaussian process prior on this function. And what's really nice about these Gaussian process priors, and we'll see this in an example in a second, is that they're very flexible, right? So they can capture basically any arbitrary function, and they've been shown to work very well empirically. We're going to see that they have some major drawbacks in terms of computation, right? Some of those can be alleviated, but let's talk a little bit more about them first before we talk about any issues that they have. Okay, so notationally, if you want to place a Gaussian process prior in this function, which you could write, which you might commonly see as something of this nature, is that you say that this function follows a Gaussian process with mean function mu sub j and kernel function k sub j. Okay. You can think of the mean function as kind of a best prior guess at what the function is. So you could center this function. You could say, oh, well, maybe I want to allow for deviations from linearity, but I could center it at a linear function. So I could let the mean function be a linear function of the covariate, right? but the Gaussian process will allow for deviations from that. You could also just specify it to be the zero function, right? Just center it at zero, and then again, we'll see a posteriori that it can update to very flexible nonlinear functions. I think the real key here is this kernel function. So you might have seen kernel functions in other contexts, such as like support vector machines or kernel regression or local regression, and it has a similar sort of flavor here, right? In that the kernel function, it reflects sort of similarity or distance between two predictors. So this kernel function takes in two inputs, right, which are just two values of the covariate xj, right? And typically what it is that if xj and xj prime are very similar or very close to each other, then the kernel function will be larger, right? So smaller distances between the two predictors leads to larger values in this kernel function, right? So you can think of the kernel as intuitively representing how similar two covariate values are to each other, how close they are to each other with respect to some metric. All right, what this actually implies, and what I think is an easier way to see this, is that for any finite collection of points, right? So let's think of the n points that we observe in our data, right? So xj1 through xjn, this Gaussian process prior would assume that any finite collection of points like this follows a multivariate normal distribution with mean at the mean function evaluated at the n data points, and covariance matrix, which I'm going to call sigma j here. Right? But the covariance matrix here, sigma sub j, right? The individual elements of this covariance matrix are just given by this kernel function. Right? So what this means is that if 2 points are very similar to each other, right, then they're more correlated with each other. So essentially, Gaussian processes rely on some degree of smoothness. It relies on this assumption that if 2 points are nearby, they'll have similar values of this function. If they're very far apart from each other, then they won't necessarily have similar values. Right? So what that's essentially imposing is just smoothness. Right? So it's going to allow for arbitrary amounts of nonlinearity. You don't have to specify what that nonlinear function looks like. Right? And it'll work well if that nonlinear function is smooth. Okay? All right, and the degree of this smoothness, how smooth your resulting function is, depends on the kernel function. So that's what you do have to choose in Gaussian process regression. Right? You have to choose a kernel function. Right? So a common one is the Gaussian kernel. Again, so this part of the notes, we're not going to go into too many details in the weeds. So we're not going to go into the kernel function too much. Right? But you have to choose one. There are a couple of standard choices. And then there's a hyperparameter in the Gaussian process kernel, which dictates how smooth it is. So why these things are useful and why we like them. So here, I simulated an example where the true function was very nonlinear, right? The truth is something that looks kind of like a trigonometric function or something of that nature, right? This red line. But what I see here is that my black line, which is the posterior mean I get from putting a Gaussian process prior on this function, centers around the true value very closely, right? It almost perfectly gets the true function, right? And then the gray line are just the pointwise 95% credible intervals. But the idea here is that I didn't have to specify that the function takes a particular form, but the Gaussian process was able to approximate this true function very well in this case, right? So they're very flexible and they tend to work quite well.
What kernel was it for this one?
This was using the Gaussian kernel, the radial kernel, sometimes people call it. Okay. All right. I'm going to talk to you guys about this whole course is on high dimensional Bayesian inference. Nothing I've just showed you on the past few slides is high dimensional. And so a natural question might be how one might go about using these Gaussian process priors in a more high dimensional setting, right? So we live in this high dimensional setting, but we don't want to rely on linearity. So there are a couple ways one can do this that can be embedded within the spike-and-slab prior distribution framework in the exact same way as the simpler approaches that we've already discussed. So let's let here for now this be the n vector. So f sub j of xj here is the vector of our observed locations, right? So specifying a Gaussian process prior would amount to specifying a multivariate normal distribution for them. We're going to use the 0 vector as the mean here. So we're going to use a 0 mean function. But this covariance matrix is given by that kernel function, whichever one you choose to use. And then you're scaling it by this sigma parameter here. So if I want to embed this within the spike and slab prior distribution framework, there's a couple ways I could do this. The first, so one paper that sorry about that. One paper that I've seen this used in is this Brian Rich paper in 2009, right? That they used Gaussian processes to do variable selection in a high dimensional setting. They said, you know what? We're going to have this variance component here, and we're going to put a spike and slab prior distribution on that component, right? So either that variance component is 0, so it comes from a point mass at 0, or it comes from some continuous distribution, which I'll just denote with G here. So G here could be any continuous distribution that lives on the positive real line. This is a variance parameter, so it has to be positive, right? And so in that paper, I think they used a half Cauchy distribution, right? But anything that assigns weight to the positive real line would work here, right? And so intuitively, this does the exact same thing. Even though it's a little bit different, we no longer have a normal prior distribution for the slab. It's the same idea, right? You have a spike to account for the fact that some of these covariates don't matter, right? And so some of these are going to have variances that are equal exactly to 0, and they're going to be washed away from the model completely. If, on the contrary, gamma j is equal to 1, then this variance component will be positive, and we'll update this from a Gaussian process. Okay. So at least at a high level, it's doing the same thing as the previous approaches with spike and slabs. Another way that one can do this that could be implemented very easily is just to directly place the spike and slab prior distribution on this vector of this n vector of function values at our observed locations. So again, we can put a spike and slab prior distribution on this. We can make the spike a vector of zeros. So that would mean that this function is 0 for every individual. So that covariate is completely removed from the model. Or we can assume that it comes from a multivariate normal distribution, right? With the covariance matrix given by this kernel function of the Gaussian process. Right? And again, this has the same feature as all of our other spike and slab prior approaches, in that either this function is completely zeroed out or it's completely non-zero. Okay? But what's nice about either of these approaches to doing this is that if you specify gamma j in this way, it has the exact same interpretation as in the linear setting. Right? Gamma j corresponds to variable importance metric. Right? So I can look at the posterior distribution, the gamma j equals 1, or the posterior probability that gamma j equals 1, to see how important a particular covariate is, right, for predicting the outcome. Right? So gamma has the identical interpretation as it did in the linear case. Just now, if a function gets included in the model, if it's deemed important, instead of including it linearly and updating its beta coefficient, it's included as a Gaussian process, and it's allowed to be a nonlinear relationship on the outcome. Now, one might naturally think that this is far more complicated, right? Maybe you've never seen nonparametric Bayes before, and you say, well, I'm sure that this sounds more complicated. It's sort of arbitrarily flexible. I'm sure updating it is very difficult. But it turns out it's actually not very difficult. Updating the gamma j's is actually equally straightforward as it was if you use the sampling trick that we did before. Essentially, you do the same trick as before, right? Where I introduce, instead of now the notion that beta was equal to 0 from before, I introduce the notion that these functions are all equal to 0, which sort of intuitively works the same way. It's like excluding that covariate from the model, right? And if I follow the exact same algebraic steps that I did previously, I again get a ratio of densities, right? Scaled by tau, right? And the numerator is again the normal, right? It's the normal density at 0, given your covariance matrix, that your observed data would all be 0, right? Whereas the denominator is your posterior density of your data being equal to 0, right? So if the data strongly suggests that this function is non-zero, right? Whether it's linear or not, this denominator should be very small, making this expression large and more likely to include this covariate into the model. Okay. So as with before, the only thing that you have to do in this situation to calculate this quantity is to be able to calculate this. And this is where the burden comes in for Gaussian processes. Calculating this m and this v, which was very easy before, is now computationally very difficult. It's not difficult, I would say. It's very easy, actually, algebraically to write out what these expressions are, right? But they involve an inverse of a very large matrix. And in particular, they involve an inverse of an n by n matrix, where n is your sample size, right? So while these Gaussian processes are very flexible, and that, as you saw right in the empirical example, I gave it a very weird but smooth function, and it still captured it very easily without me having to specify anything other than this kernel function. Right? But this computational burden was very heavy. Right? I had to invert an n by n matrix, and what's even worse is that you have to do that at every single iteration of an MCMC. Right? You don't just have to do it once; you have to do it many times. And think about this: if we're in the high-dimensional scenario, and I want to have one of these for each covariate, I not only have to do this for every MCMC sample, I have to do it for every covariate. And so the computation just explodes with the sample size, right? Because inverting an n by n matrix has order of operations n cubed in terms of how many operations it requires to invert it. Now, there are some computational tricks to speeding that up a little bit, but there's no way to make it fast, right? This is going to be computationally burdensome. So there have been a couple of approximations that have been proposed that work really well. So I pointed to a few papers here that talk about how to speed up Gaussian processes, right? And so I point you to that work if you want to use those. So there are some ways to alleviate this issue, and these spike-and-slab prior distributions could be embedded within those frameworks easily. But nonetheless, it's always going to be somewhat computationally heavy. So if computation time is a big concern for you, then you can simply use the basis function approach, right? It's a parametric approach, but it's a lot weaker than assuming the linear assumptions that we had from the first part of the course, right? The computation speed in this is much closer to the linear model than to the Gaussian process model. It's hardly any different from the linear model, right? So it's not as flexible as the GP. It lives in the middle of these two approaches, right? It's more flexible than the linear model, but less flexible than the Gaussian process. But it's more computationally heavy than linear regression, but only a little bit, and much more computationally efficient than the Gaussian process. But now this is kind of where I segue into Tony's portion of this short course, is that this is still making additivity assumptions, right? So I'm assuming that the impact of one covariate on the outcome does not depend on the values of the others, right? Which may not hold. And so we want to alleviate that assumption. So there actually has been some work done in Gaussian processes in this paper here, in 2014, where basically they represent this mean function of y given x as a sum of Gaussian processes, so an additive function of Gaussian processes, but they do variable selection such that within each of these functions, so that each of these functions contains a subset of the predictors, but it doesn't have to be a single predictor, right? There can be two predictors in a particular Gaussian process, allowing for interaction between those two predictors, or even higher dimensional interactions. So it doesn't assume additivity like the approaches that we've seen so far do, right? But now I'm going to point toward Tony's work, because that's where the non-additivity stuff really works quite well and has really been shown to be quite powerful, but I'll let him talk about that. So the references for this portion of the talk are here. And I will leave it to Tony, and I will man the chat now.
Okay. Well, I think there's a question that I didn't answer in the, which is actually a really good one, which is kind of the, how does the fact that Gaussian processes or even basis function expansions, the fact that there is a group of betas, what sort of implications does that have for the variable selection?
That's a great point. Yeah, so it's a trade-off, right? So it's not a free lunch, right? You can't just get this nonlinearity without losing something. So it's kind of a bias variance trade-off, right? You're reducing bias, but at the cost of efficiency, right? You're doing something that's more flexible and less efficient. And I think what that happens to lead to, and it's very easy to see this empirically, is that you tend to get less power as you increase so the linear approach will have the most power, right? But might misspecify these true functions. The basis function approach will have less power than the linear one, but is less likely to misspecify the estimated functions. And then the Gaussian process in the extreme is going to have the least power to detect important covariates, but it'll make the least assumptions and have be least susceptible to biases, right? So it's all a trade-off. But you're absolutely right that you lose power when you go to these more flexible approaches. That's absolutely an issue. So that's a great point.
But it's not necessarily a mathematical law that there must be some trade-off. If, for example, the function was, was sort of a correlation, non-linear, but maybe has, non-monotone, and so it kind of the univariate one maybe estimates a flat line or something.
Yes, that's
in that case,
true.
maybe you would only be able to pick it up if you use something non-linear. But I think that's not usually what you expect.
Yeah.
Usually,
so as a general rule of thumb.
As a general rule, yeah.
Yeah, but absolutely, Tony's right that if you have some functions are weird, and if the best linear approximation to them is a flat line, and so the true beta, right? So if you fit a linear model, the true beta is like the best linear approximation to that function will be very close to 0, and you won't have any power to detect it. But generally speaking, the Gaussian process will have lower power, except in situations like that, where the linear model does such a poor job approximating the true function that it actually thinks it's close to 0.
There's another, yeah, so you did a good job of kind of, discussing this. If there's this basis function approach on the one hand and the Gaussian process approach on the other, referencing some computational tricks. In the case of one dimension, it's not too bad. So you actually don't have to choose between those two in some sense if you're willing to do some approximation. So you can approximate a given kernel with some basis function expansions as well. Often those Gaussian process approximations turn into basis function approximations. So these low rank approximations to Gaussian processes. Probably there's some references that we have.
I think certainly one of the Banerjee references that I gave talks about that.
Yeah. Yeah, certainly the spatial folks have done a lot of work on that. And then someone wants the slides. The slides are,
yeah.
I'll throw them in the chat again. So Joey's are in what is this, HD Bayesian modeling.pdf. All right, did we want to take a break? I'm guessing people probably want a...
Yeah, let's take a few minutes, I think. Maybe 5 minutes, everyone, and then we'll come back at...
that seems quite...
all right, 3 minutes, 3 minutes.
All right, any
10
votes
minutes, I don't know, I thought you were...
Any votes on how long we want to take a break? I thought people might be burned out by now.
Anybody want to give it?
No one wants to make a suggestion.
10,
Alan wants 10. Alan has seemed reasonable so far. So
all right, we got multiple votes.
We'll do 10. All right.
All right, so guess we'll come back at 11:27 Eastern time, roughly.
My wife somehow locked herself out of the house, and I haven't been able to get my hands.
Good timing for the break.
I'm gonna go fix
Okay, if anybody has any questions, I can take them. I have to take a quick break, but I'll be back in like 2 minutes. If anyone has any questions, feel free to put them in the chat, and then I'll try to address them then. All right, see you a second.
If anyone does want to ask any questions in the meantime, please feel free to.
Yes, so just to the question here, there should be a recording posted. So I don't know if one of the ISBA people that are in attendance want to chime in exactly where that can be found. I don't know exactly where the link will be to that, but I'm sure they can send you a link to the website that you need to go to find this recording, but it is being recorded.
It's been about 10 minutes, right?
Yeah, I think we can maybe give
All
it
right.
one more minute.
Well, I'm going to see if I can get all the screen stuff taken care of. As you can see, my desktop. Yes. You can see Joey, or no?
I can see you. You're on the GitHub page.
Okay.
Yeah.
All right. Yeah. Yeah, I'm just sharing the whole desktop. And as far as our code, is this big enough?
I can see it. Yeah, I think it should be. Let the panelists answer.
Okay.
And I will say to the panelists for this, Tony did a great job answering questions throughout my portion, and I'm going to do my best to do his. But this is real work that really he developed, and he's really the expert in this stuff. So I'll do my best, but when need be, I'll just interrupt you, Tony. And
you're very kind with attribution. I think you know, Ed George and Rob McCullough might have something to say about me. me being.
I'm not saying you're the only expert in BAR.
Yeah,
I'm
yeah.
saying in the high dimensional extensions to BAR, your work is really kind of pushed forward stuff, I think.
Could I put a white background in R? Oh, okay. So yeah, I can do that. Let me see here. I guess this is hard on the eyes. Let's see. What's a good, the Xcode one? Is that an improvement? Take the default. All right. Well, we can get started, I guess. So I'm a big, I don't know. I like code and stuff. So I thought Joey's stuff. I think the idea was to sort of give you guys the tools to be able to implement these things on your own in whatever kind of models you're interested in building. But I'll just give a couple of pointers to some packages that you might be interested in, just knowing that they exist if you're interested in using these in more of a, you know, if you're interested in more conventional applications. So there's a great package called spike-slab. Just regular spike-slab. I guess it's not installed on mine, but here's spike-slab or spike.slab. That implements a lot of the just generic spike-and-slab stuff that Joey talked about, possibly with different MCMC details. And then if you want to do a GAM, there is a package called spike-slab GAM. I can't quite remember which one they used. I believe they do the basis function expansion.
They do.
To do the GAM. So just a couple of packages that you might give a, you know, if you're just interested in trying things out. Those are two good ones. And then there's one that does Bayesian model averaging, although I can't quite remember the name of it off the top of my head.
The R package to do Bayesian model averaging?
Yeah. Well, there's one that does like a Liang Berger, that whole thing with G priors. Like maybe BAMF or I don't know. All right.
I think there's a package called BMA that does.
BMA, maybe that's the one. Yeah. Okay. Yeah, that one does it in a slightly different framework. But if you're interested in coding along with me, so I pulled up the GitHub page. All of my stuff is in here, and it's organized from sort of 1 to 6 as you move through it. So the idea when you start with 01 and you end with we'll end with 06. And inside the install file, which is here, is just a list of all the packages that you And if you want to code along, these are the things that you'll need. I use tidyverse and caret for just a couple of things. These are good to have kind of regardless. Probably these days everyone has the tidyverse installed. And caret is just used for convenience for data splitting and stuff, although it offers a lot of other stuff as well. And a lot of these packages are kind of tricky to get installed. Not all of them are on CRAN. I mean, I'm responsible for some of them not being on CRAN, but you should be able to do just about everything with just this single package called BART. So unlike with a lot of the stuff that Joey talked about, these are not so straightforward to implement. So I'm going to be talking about Bayesian decision tree ensembles. Implementing them is non-trivial, although it's a fantastic coding exercise. But generally, I think most people don't have the patience for sort of coding these things up themselves. And so we're going to do a more package-oriented presentation of the main ideas. All of this stuff is available in this package BART. So you can do that. It's a little bit slow. So I'm going to be using a different package just to, have things progress a little bit more quickly and use a more efficient implementation of these ideas. They require the R-Java package, which is, this is kind of the step where a lot of people might have problems installing stuff. So you have to have Java on your computer, and then there's all sorts of configuration issues that you might have some issues with. And then you have to install my package, which is available up on my GitHub. But if you're able to get that working, that's great. And this is a fork. So my package, Dart Machine, is a fork of another package called Bart Machine, which is on CRAN. It might be epsilon easier to install than mine, but it still has these R-Java issues, and so it's not. There's a non-negligible risk of some problems. And then I have another package that implements a slightly different variant of the ideas I'm going to be discussing. I don't think I actually use this one in any of my slides. Yeah, again, it's a little bit slower than the stuff I'm going to be using, but it is there. It's yeah, a little bit fancier take on some of the ideas that I'll be talking about. And then there's another package that can be used for variable selection, adopting sort of a very different take on variable selection than what we presented here. So Joey and I have sort of stayed in the framework of fully Bayes variable selection, where you're interested in doing the model selection within the context of a particular Bayesian model, using these indicators and stuff. That's not the only way you can do Bayesian model selection. And so this other package by Rob McCullough implements another take on it. That's also been very frequently used with these models. And we'll discuss that time permitting. We'll discuss this package and the associated methods. But okay, so I'll jump into the material here. So what I want you guys to get out of this are, so this is exclusively about Bayesian decision tree ensembles as a tool for performing variable selection in nonparametric, non-additive settings, potentially in high dimensions. This isn't the only thing that we could have that we could talk about. So the literature is quite large on all these, sort of fully non-parametric methods for variable selection. So this is sort of a selective set of things. We certainly could have talked more about Gaussian processes. So Gaussian processes for non-additive models. And then there's a bunch of interesting work in Bayesian non-parametrics more generally, using things like Dirichlet process mixtures or various stick breaking processes that we could have talked about. There's really like no end to the set of stuff that's been proposed. But I like this stuff, and not not just because I work on it. It's also very friendly. It's very user friendly. So my hope is that you'll be able to actually use these ideas, use the software, and be able to implement things with very, very few headaches. So with that being said, I'll just jump into it. So what I want you guys to do or be able to get from this is to basically know what these Bayesian additive regression tree models are, and sort of understand, one, how does it differ qualitatively from the methods that Joey talked about, and under what situations might you want to use these methods. And you should be able to apply BART in nonparametric regression and classification problems, as with Joey's material. We'll focus just on the case of nonparametric regression, but understand like everything that I'll talk about can be ported directly into classification problems, can be used in survival, count data, basically any setting that you would be interested in. You can shove one of these models in there. And then basically applying these models to perform, so one, BART, and to perform variable selection, but also various extensions that I'm going to be giving you that allow you to embed BART into these fully Bayesian variable selection approaches that we've been talking about. And then again, time permitting, we'll talk about a slightly different topic, which is very much related to variable selection, but is not quite the same thing, which is interaction detection. So a first order question you can ask about a collection of variables is which one of these are important. That's probably often among the most important questions that you would ask, but you may also be interested in knowing how variables interact with one another. And so does variable A, if I vary it, does it change the relationship between variable B and the response? So these are outside the scope of the additive models that Joey discussed, because it sort of imposes a lack of interaction structure in the GAMs that he discussed. But it is an option, and we'll see a problem in which there are some very kind of interesting interactions that you can pick out of an analysis using these methods. So I'll start with just a picture of what a decision tree is. I think intuitively, we look at a picture like this and you kind of immediately know what's going on, which is one of the appeals of tree-based methods. It doesn't take a lot of explanation to kind of understand what they're doing. This is a decision tree for predicting the salaries of baseball players in a particular season. Although, I guess if I was being true to the international spirit of ISBA, I probably should have gone with soccer or something more international. But the basic idea here is some features of particular baseball players, and you sort of just iteratively check these rules, you mosey down the tree, and eventually you hit one of these things that we call leaf nodes. So the nodes sitting inside the tree that have decision rules, I'll be referring to these as branches. And the values down here at the bottom, I'll refer to as leaves. So at each branch, I apply the rule. It's a yes or no. So yes, let's say I scored less than 46 runs, and I know I'm not a free agent, and I score no, I do not score less than 28 runs, meaning I score more than 28 runs. That would point me down to this node here. You guys can see the cursor, right? I think you can. And this would give the salary in thousands of dollars in this particular example. So for that particular individual, I would predict a salary of about $1.5 million. And the way that this connects to variable selection is that you can see if I don't split on a variable, then it's sort of automatically not, that's kind of equivalent to doing variable selection. So it's slightly different from the spike-and-slab approach that Joey discussed, although you certainly can use the same type of spike-and-slab ideas. Those ideas do play a role in what I'm going to be discussing. But the tree by itself on its own does give you some degree of variable selection just by what I choose to split on. So there are other variables in this data set that were not used to construct splits, and in some sense, those have not been included in the model. Now, associated to each decision tree, an alternative view of these things is I could map a particular decision tree to a partition or a step function on the predictor space. So here is a simple case where I have two variables, x1 and x2. We'll say they live on 0, 1, so they're both on the unit interval. And I can take this decision tree, and again, I hit the bottom, these leaf nodes, these have predictions associated to them, map that to a step function on the covariate space. So if I'm, let's say, less than 0.4, but bigger than 0.7, I get mu2. So I get all of the values that kind of live in this region here. So there's this, yeah, just a one, I shouldn't say one-to-one. There's actually many different trees that are associated to any particular partition. But if you give me a tree, I will be able to build for you a step function. So I want to, yeah, I should say that, you know, decision tree methods are not by any stretch exclusively Bayesian. In fact, the tradition of using these methods is mostly not in Bayesian. In Bayesian circles, it's sort of the more data science or machine learning folks who really use this a lot as part of their toolkit. So some other methods. I divide these up into two basic categories of methods. First is the sampling methods. The sampling methods were, I think, I'll just attribute them essentially to Leo Breiman, who introduced the idea of bagging decision trees, which there's lots of different ways of constructing these decision trees. Often they're constructed in a greedy fashion using what's called the CART algorithm. Breiman introduced this idea of bagging many different decision trees together. And I guess I should have said this already. Generally, you don't want to use a single decision tree. So there are very, very good reasons for not wanting to just use one of these things. Generally, you want to use a whole ensemble of them. And that's for a variety of reasons. One is if you these estimators tend to be very unstable. And what I mean by that is, let's say that I have my data set, I fit this decision tree, and then I do something like bootstrap the data. So meaning I resample with replacement from my original data set. If I build a new decision tree, there's actually a fairly good chance that I'll end up with a completely different structure. So they're highly unstable under slight perturbations of the data. And because of that, they tend to be very high variance estimators if you use something like CART. And one way, or a very nice idea by Leo Breiman, was to actually leverage this instability to produce better estimators. And essentially what this idea of bagging does is it resamples the data many, many times and builds many different decision trees on the data, and then averages the predictions of each of the individual decision trees together. So that approach is called bagging. I could give more detail, but we're not going to be doing bagging, so I won't. So there's the idea of bagging, and then there's kind of its older brother, also came up attributable to Leo Breiman, which is to induce additional randomizations to the algorithm for constructing the decision tree that leads to these things called random forests. Extremely popular algorithm. Basically, it's just bagging with some additional randomization built in that we won't worry about. So those are two extremely popular techniques. And then if you want to take the Bayesian viewpoint, there's nothing to stop you. You know, if I want to fit a decision tree like this from a Bayesian perspective, I mean, what's a Bayesian going to do? They're going to write down a prior distribution on the space of decision trees, and then just run a Markov chain Monte Carlo to fit the thing. So that's while it's a little bit, I think, strange at first glance to think of Bayesians fitting decision tree models like this, conceptually, there's nothing weird going on. I just need to write down a prior on the space of decision trees, and then run MCMC as usual, as long as the decision tree gives me an actual generative model for the data. So that's attributable to Chipman, George, and McCullough in this seminal 1998 paper, and also Dennison, Malik, and there's another person that I'm forgetting on this other paper, but two papers introduced the Bayesian card essentially concurrently, using the same sort of basic idea of just writing a prior distribution on the space of trees. And I'll discuss what a prior distribution on the space of trees actually looks like in a few slides. So that's the first class of decision tree ensembling methods. And then there's another class of decision tree ensembling methods that I think of as being separate, which is combining weak learners. So in the case of sampling methods, the idea is basically to fit a whole big decision tree to my data, and then average together many different big decision trees. Each of the decision trees itself should be a good estimator of the underlying signal. So if I have this, I can already get good predictions, and then the ensembling is just a bonus on top. I'm taking a good predictor and I'm making it better by doing bagging, random forests, or Bayesian model averaging. The weak learner idea is fundamentally different in that I have an army of decision trees, but each individual decision tree by itself doesn't actually do a very good job of predicting the outcome. It's a so-called weak learner. The idea of looking at weak learners was initially proposed from the standpoint of what's called boosting. So it's boosting weak learners, and an extremely popular technique. If you take part in Kaggle competitions, boosting algorithms often do extremely well. This idea of boosting decision trees. And BART, the method that I'm going to talk about, falls more into this weak learner category of taking a bunch of decision trees that by themselves don't do a very good job and combining them to produce a good learner. So the gold standard is still, even though this is ISBA, the gold standard in a lot of data science problems is actually just doing boosting. It wins competitions and has a bunch of very, very nice implementations, XGBoost being one of the popular ones. There's a lot of great BART implementations as well. All right, so now I'll talk about the BART model, and it's a relatively straightforward idea. I have an underlying function R, or what Joey was calling F, that I'm interested in estimating. So this could be the mean of some model. I might have a model y equals R of x plus epsilon Gaussian error. What does my R look like? And it's just a sum of a bunch of decision trees. So I take, let's say I have 200 of these guys. I plug in my predictor down the first tree. It gives me a prediction. I plug something down in the second tree. It gives me a prediction. And all I'm doing is I'm taking those individual predictions of each of the decision trees and adding them together. So each tree, if I want to do Bayesian inference, I need to write down a prior distribution on each of these trees. And so the prior distribution on the trees, that's going to be two things. It's going to be, one, what is the shape of the tree? And two, what are the decision rules of the tree? So there's two components to each of these decision trees. It's what's the shape of the tree and what are the individual rules. In addition, I have my leaf node parameters. Those are the predictions from the individual trees. I need to write down a prior for those as well. So formally what's going on, if you don't like my picture here is I'm decomposing R as a sum of capital T T trees. This function G here takes 2 arguments in addition to X. So it takes my covariate in. It also takes in the decision tree and the predictions of the tree, and returns the associated. This is just a step function, right? So this is each individual G is a function that looks like this, just a step function. So if you're an alternative way of kind of thinking about this, if you are more versed in basis function expansions, you could think of this as an adaptive basis function expansion, where each of the basis functions is just a step function on my collection of predictors. That's an alternate way of kind of thinking about it. But unlike in Joey's setup, where it's fixed basis functions, these are our basis functions that I'm learning from the data itself. Now, what does it mean to add decision trees together? Why would this be expected to actually make anything better for you? The operation of adding decision trees together, you can look at it directly in terms of those partitions or those step functions. I like to think of these as kind of being transparencies. You know, if I take a transparency and I draw a line down vertically, I draw a line down horizontally, those define 2 partitions, and then what it means to add them together is kind of just overlaying one transparency on top of the other. And so if I have a tree that has predictions mu1 and mu2, I have a tree that has predictions mu3 and mu4, I overlay them on top of each other, I get a new partition. But it's a partition for which the predictions have been smoothed together. So if I look at this cell here, I have mu1 plus mu3. Why? Because there's a mu1 in the left quadrant over here, or left half plane, and a mu3 in the upper half plane here. So in this region, I'll get mu1 plus mu3. In this region, I'll get mu2 plus mu3. But now notice there's a correlation between these 2 cells, because if I put a prior on mu3, then these 2 cells are going to be correlated with one another. So what this addition of decision trees is buying us is actually some additional smoothness. So I'm smoothing together the predictions for each of these cells of my partition. So there's a correlation between these 2 through mu3. There's a correlation between these 2 through mu1. And then these 2 cells in the top left and the bottom right are uncorrelated because they don't share any of the parameters. Now I'll talk about what the prior distribution on these trees actually looks like. This is an algorithm for simulating from the prior. It's a lot of text, so I'll illustrate the concept just essentially through a picture. So this is a description of the prior, and it's not a description of how you sample from the posterior. So this is like a question that gets asked sometimes, or this is just a description of the prior distribution. The posterior is much more complicated, and you sample it with MCMC. To sample from the prior, you start with a tree that has no nodes. So you start with a completely empty tree, and then you just kind of grow. So I start at the root, and then with some probability, I decide that the root is going to be a branch. So I don't know, with some probability Q, this root grows into a branch. Now there are 2 leaf nodes. And associated with the root is some decision rule. So I grow from here to here, and I have a new associated partition. And then once I've done that, I then advance to the next layer of the tree. So this is a depth 0 tree. This is now a depth 1 tree. And I look at all the leads of depth 1, and I basically just iterate the procedure. So with some probability, this guy is going to be turned into a branch with 2 children. let's say that I stop. So when I go from here to here, I decide to terminate this one. That becomes a leaf. And then the right one, I maybe decide with some probability that one is going to grow again. So it splits. Now I have a new tree over here with a new decision rule. So this first one split on x1, the second one split on x2. I now have this this partition, and I iterate the process again. I have these two nodes down here, and then just for the sake of simplicity, let's say I stop on both of them. So now I have my tree. After I have the tree, I go ahead and I sample the mu1, the mu2, and the mu3 from their prior distribution. Which once I have the tree, just take that to be a Gaussian. So just a normal prior on these leaf nodes. This is the same idea, just expressed in words instead of pictures. So I initialize the root. It has depth d equals 0. And then for each node of depth d, you convert it to a branch with some probability, gamma divided by 1 plus d to the beta. The probability of stopping each time is not restricted to just be not restricted to be constant. Actually, you probably don't want it to be constant. You want to make sure that the tree actually stops growing. Right? It would be bad if you grew a tree and it just grew forever. This form of the prior distribution ensures that the tree is going to terminate at some point. But okay, you convert each of the nodes at depth d to a branch with this probability. Otherwise, it stays a leaf. If all of the nodes of depth d are leaves, then you are done. Otherwise, you return to the previous step. After you've sampled the shape of the tree, you associate to each coordinate, so each of these nodes here. You need to pick which variable it's going to sample on. You're going to split on. So you do that here, and you sample each predictor. So I choose x1, let's say, as my variable to split on with probability s1. Or if I have variable x2, I pick that with probability s2 from the prior. So s is giving me the prior probability of splitting on each of the individual predictors in my model. So s is actually going to play a pretty important role for variable selection, as we'll see. Once I've picked all of the splitting rules, I then pick a cut point. So I have a cut here. I cut on 1/2, let's say. Over here, I cut on 1/2. It didn't have to be 1/2. And that's what this step is doing. It's basically saying, sample from the observed x's that lie in each node a new cutting point. And then you terminate the algorithm at the end, just a normal prior on the leaf node parameters, and you end up with a step function that looks like this. Okay, so I have my prior distribution. These models have worked very well in practice for a lot of different types of models. We're going to stick exclusively with this semi-parametric Bayesian model, semi-parametric regression model, where my y is r of x plus some error.
Tony, there's a quick couple questions in the chat.
Not going back to previous one. All right, hang on. I think I missed.
There's a question before that first about whether predictors are sampled with or without replacement in that construction.
Predictors are sampled with replacement. So you're allowed to split on the same variable more than once. And then can you not, going back to previous slides, is this like is this a whiplash question? Like don't scroll too much through the slides. Gonna have to.
I'm not sure. I think it's okay what you're doing so far. Yeah.
I'm okay. All right.
Yeah.
All right. Yeah, maybe clarify if there's too much whiplash from me going back and forth through slides. Let me know. I'm not entirely sure if that's what you're asking. But all right. So I have my semi-parametric regression model. That's one option. It's no difficulty to embed this in a probit regression problem. So you do some sort of fairly standard data augmentation, and you'll be able to do probit regression, no problem. And then it's been extended to other types of models. So you can do Poisson log linear models. You can do Cox proportional hazard model. You can do fully non-parametric density estimation. You can basically do anything with these types of models. There's software for doing anything you want. I think I forgot to even give a reference to the paper that introduced this, which is Chipman, George, and McCullough, 2010 in Annals of Applied Statistics. So that's the paper that introduced these BART methods and is responsible for all the prior specification, all this stuff. It's straight from that paper, which there should be a reference to at the end of the slides if you want to go dig up the original reference. The extension to Poisson log linear models is a paper by Jared Murray that does that. And if you're interested in a particular application, let's say, you can email me and I'll be happy to tell you where you can go about finding the papers for it. Tons of other possibilities. Another really slick version of this actually is the heteroscedastic version, which also puts a BART model on the variance component of the semi-parametric regression. Lots of stuff you can do. And part of the reason that these things are so useful in practice, or so easy to use, is that there are a collection of default hyperparameter values that you can use that just seem to, for whatever reason, they seem to work very well. So people often don't have to think about how you go about slapping down these priors. It's an interesting contrast from, a lot of Bayesian non-parametric methods where maybe you have to think about these things a lot. Most of the time when I'm using these things, I just plug in some defaults and I completely forget about it. So these are particular defaults that are used for semi-parametric regression. These parameters in the tree, so these gamma and beta, that corresponds to how you grow out the tree. You just, from up on high, specify 0.95 for the gamma parameter and beta equal 2 for the beta parameter. And I've never played with these parameters beyond that. Maybe I'm being overly ambitious, but I've never found any need to ever do anything else. The other two priors I have tried other things on, and these also just seem to work very well in practice. So for the semi-parametric regression setting, the trick is to standardize your response to lie in the interval -0.5 to 0.5, and then you just use this prior, which is the leaf node parameter is normal, mean 0, and variance 1/4 times the number of trees. And it is important that you scale it by the number of trees, but any software that you use is going to do this for you automatically, basically. So do that for the leaf node prior, and then I also have a prior on the variance, sigma squared. The default on that is just an inverse gamma prior on sigma squared. Alpha chosen to be 1.5 and beta chosen in some kind of empirical way from the data. Basically, you construct an empirical estimate of sigma by fitting a linear regression, and then choose the prior so that your sigma is centered, chosen to be less than that with some probability. What is 1/4t in the mu TL prior again? So UTL, that's the prior on, that's the prior on the predictions, those leaf node parameters. And then the variance of that, T is the number of trees. So there is another tuning parameter in here, which is the number of trees in the model. And T is the number of trees. And this is 1 divided by 4 times T. Like, so I guess I should have a parentheses around the 4 and the T, but yeah, it's for reasons that I won't go into. It's important that you divide by T, but any software is going to do that for you. These seem to work very well. If you want, you can do cross-validation. That's another thing that people have done. If you're worried about it, if you're paranoid about just shoving defaults in here and not thinking critically, you can do cross-validation. So this is some boilerplate code for installing the packages. It's just the same thing as this. Hopefully, if you're planning on following along, you've been able to install at least one of these packages, hopefully. But I'll run all the code as well. So I'll say something about the different models or the different packages. How do they differentiate between themselves? So there's the package BART, written by one of the people who introduced BART. There's a package that I wrote called SoftBART, and another package that I wrote called. All right. Sorry. Do you have to specify T prior in your calculations? If yes, is there an? So this is a good question. I'll just read out the question aloud. So Raphael asks, do you have to specify a prior on T? And if yes, is there an issue with using really large T? So usually you do not specify a prior on T, you fix it. You can specify a prior on T. You can do some sort of reversible jump. You can do a reversible jump algorithm, put a prior on T. That's possible. My understanding is that people have tried it and have not been successful. I have tried it and have not been successful at actually getting that to work. So people don't usually put a prior on T. But that means you do have to pick a value for it. And the tradition along the lines of these defaults is to pick T either to be 50 or 200. So those might seem a little bit large and arbitrary as well. And they seem to work well for all the problems that I work on. And another option is to cross-validate. You can always do that. Is there an issue with using really large T? And actually, the answer to that, surprisingly, is no. You can take T equal to infinity, and nothing will go wrong. And the reason that it won't go wrong is actually because you've normalized by T in the prior on mu. So you might say, well, if I send T off to infinity, I should be overfitting. But actually, if you send T off to infinity, you're applying more and more shrinkage to these parameters. And it can be shown that if you send T off to infinity, the prior distribution actually converges to a Gaussian process. So you have a well-defined limit as you increase T off to infinity. So for that reason, you can think of, if I send T off to infinity, the worst thing that will happen is that I approximate a Gaussian process. And so, I mean, I can give a heuristic proof, which is that you're summing up a bunch of stuff, and the central limit theorem says if you sum up a bunch of stuff, you go to a Gaussian. But to get that Gaussian, it was important that you divided by T. That's equivalent to essentially dividing by 1 over the square root of T here, which is why the central limit theorem applies. But okay, so how do these packages differ from one another? So BART is a package. It's on CRAN, so that's a reason to like it. They're held to some sort of standard for staying on CRAN. It's a little bit slower than some of the implementations that you could find out there, but it implements the stuff that I'm going to talk about, and it's, I mean, these guys are pros. It's a very good package. These two I made, and so how you feel about them probably depends a little bit on how you feel about me. Actually, I didn't make Dart Machine. This is a fork of another package that's also on CRAN. That package is also very good. It's called BART Machine. So I threw this together. It's not very well documented for what it does. BART Machine is fantastic, but it doesn't quite do everything that we're going to talk about. And then there's another package that I wrote called SoftBART, which does a slightly fancier version of BART. It's a little bit slower, but it seems to do better in terms of prediction. You can do everything that I'm going to talk about using one of these two packages. So BART, probably most reliable of them, and you can do everything. So yeah, now I'm just gonna jump into, well, I'll try to make the case that these things really are as easy to use as I've been saying. And this is just, I'm gonna do this purely from the standpoint of prediction. So how well these things do just in terms of prediction before even talking about variable selection. This example is done with the package BART Machine. So I'm going to load up my packages here and make a function for computing a root mean squared error. I'll use that. Well, maybe I don't even use that in this one. All right. And the data set that I'm going to illustrate on is this famous, at least if you're a machine learning person, famous data set called the Boston housing data set. It's built into the math package, which I think is bundled with R. But it's the price of housing. So each row of this data set, stored in here. The target of estimation is this variable MED-V, which is the median value of a house in a particular neighborhood of Boston, so a particular suburb in Boston. The median housing price in what are you measured in? You're measured in thousands of dollars. This was back from a very long time ago, so the price of houses has gone up since then. But the interest is, give me a suburb of Boston. I want to predict from some teachers what is the median housing price. And there's a bunch of variables that you could look at. So crime rate, is it an industrial place or not? What is the number of rooms in the average number of rooms in the houses there? The interest in the original study was actually on nitrous oxide concentration, the idea being that in suburbs for which there is more pollution, maybe the prices of the housing will be lower. And, you know, age, lots of things, distance from industrial centers, all kinds of stuff you could be interested in. But we don't know, we don't know whether these variables enter linearly. And for a lot of these, there's evidence that they do not enter linearly. So there's questions of which variables are relevant, are there any nonlinearities, and for the variables that do enter the model, are there any kind of interesting interactions between them? So I'll fit this, and I'll split the data into two pieces, a training set and a testing set. So this is what my caret is doing for me, my training set. So basically what I'm doing here, this thing folds, if I type it out, it's a division of the data set into 5 different folds. So these are indices of rows of the data set. And then I'm just going to take the first fold to be my testing set. I'm going to hold that out. and I'm going to train on everything but the first fold. That will be my training set. Right. As a standard for comparison, we'll just use a linear model. This is not the high dimensional setting, and so I'm not going to get in any trouble just by fitting a, just doing a linear regression, not worrying about variable selection. So I'll fit that. That's going to be our baseline for comparison. And then this incantation fits a BART model using the BART machine package. So first I give it the design matrix, and that's going to be my training set minus the median value, right? I don't want to feed the outcome into the estimation, so I have that there. The response is the median value, and then the only other thing I need to give it, as far as the model's parameter are concerned, is the number of trees. So, and I said just do 200, and so that's what I'm going to do. Aside from that, I just need to tell it, one, how many iterations do I want to use for burning in or warming up the MCMC, and how many iterations after I'm done burning in do I want to save, and then for reproducibility, I gave it a seed so that if I run the chain again, it'll give me the same answer. So I'll run that. Runs pretty fast, all things considered. You have to wait a minute. So I'll explain what I'll do after I run this is what is the correlation between the value that I predict. So this is the posterior mean. If I just look at this here, for each observation, I can get the predicted value over the chain. That's what this will give me. So I'll call that, let's just call this y hat. Take the prediction, I'll feed in Boston test. Takes a minute to do it. And so now I have my, I don't know, I'll plot my response against the predictions. And this. All right, so on the y-axis, I have the true median housing value on the x-axis, and on the y-axis, I have the posterior mean of the predicted value of each house. So it seems to do a pretty good job, and I can compare that with the benchmark, my linear regression, y hat. I run this. I see that there's a correlation on the testing set, so I'm not overfitting or anything, of about 93%. And then for the linear model, it's about 85. So at least in this data set, there is evidence that there is something to be gained by doing by using one of these tree-based methods. All right, so that's just an illustration of that that chunk of code here. And, all right. So I'll say how these are fit, and they're basically fit in the same way that Joey fit the linear models, which is essentially I do a Gibbs sampler, right? So now instead of looping over the variables, though, I loop over the individual trees. So I sample, right? Do I also get uncertainty quantification? Yes, you do get uncertainty quantification from this. So I didn't have to, I think just the predict function only gives the mean, but I can get, I can get the whole posterior distribution if I want. We'll see that in on the next slide or something. Yeah, fit by Gibbs sampling. you basically, and also the same idea, just as Joey marginalized out the betas and updated the gammas on their own, with the betas integrated out, we do the same thing here, where we integrate out the mu's associated to a tree and update the tree on its own. Now you can't quite sample from the full conditional of these things. It turns out that you just can't do that. But you can do a Metropolis Hastings update to update the tree. So you Metropolis Hastings update after integrating out the mean of the individual tree. And once you've done the Metropolis Hastings update, you sample the M from its full conditional, which, because we wrote down a Gaussian prior, is also a Gaussian prior. So this process is referred to as Bayesian backfitting. And the reason that it's called Bayesian backfitting is that each of these individual trees, it really is just a Gibbs sampler. But operationally, what you end up doing is you compute the residual holding out a given tree. So if I want to update tree lowercase t, what I do is I take the outcome, I subtract off the prediction holding that tree out, that gives me a residual, and then I update the tree using that, that residual. So the details behind this, I think, are less important, because I think most people will not be implementing this method on their own. If you are interested in detail, this paper by Kapellner and Blight, I don't know how to say his name, but goes into a lot of detail on those, on the Metropolis Hastings, on how exactly you do that, why it's the right thing to do. Just a good paper. So all right, this is the Bayesian backfitting algorithm for doing it, just for completeness, and usually done by default. There's not a lot of tuning that you do for these things either. Usually these are just left up to the discretion of whoever is designing or whoever has built the package that you're using. All right, so that's all background. If you don't completely understand everything, I hope that at least you feel like you could sit down and fit one of these things, that you're at least comfortable with, running a line like this that will fit the model for you. But now we return to the actual topic, which is variable selection. And so how do I take one of these models and use it to determine whether a variable is relevant or not? So there's a couple of different possibilities that you could use. You might say a variable is relevant if it is included in at least one branch of the ensemble. So meaning that at least one of the trees somewhere, if it splits on that variable, if it uses it in a tree, you say that it's relevant. And that's, if you're taking these models very literally, that's exactly what it would mean for the variable to be included, right? If you're in any branch, no matter how big your contribution is, then you're in the model, right? Like if you fit a regression, if your gamma is 1, you're in the model, even if your coefficient might be small. So you just have to be in at least 1. That's one option. The other option is to, rather than focusing on whether variables are relevant or not, you might try to define some notion of importance. So this would be kind of like, how big is my beta? My beta is big, it means I'm important. Well, kind of here, we'll say that if you appear all over the place in the ensemble, if there's a bunch of decision trees, a bunch of rules that use you, then we'll call you an important variable. And the initial proposals by Chipman et al. Kind of take the second viewpoint and work in terms of variable importance. So I'm going to define the variable importance as follows. It's the average of the proportion of the branches. So capital B is the number of branches in the ensemble. So B for branches. It's the number of branches in the ensemble, and MJ is going to be the number of times that you're used to split. So if variable 1 appears in 20 splitting rules, then M1 is 20, right? If variable 10 appears in 2 splitting rules, then M10 is 2. And if some variable doesn't appear in any splitting rules, then its associated M is 0, right? So the importance of a variable is just the average of the proportion of the branches that split on it. So the sum of the importances, it kind of follows, should sum to, so it's not, I don't think it's necessarily the case that it will sum to 1. But is it the case it'll sum to 1 by, yeah, should sum to 1. Yeah, so that's a measure of variable importances. Very easy to get from the model as well. So the second batch of code here looks at the variable importances. So fit the thing again. And I've changed the number of trees here from 200 to 40, and I'll discuss why I did that. Why I did that in a minute. But I can get the variable importances. For this package, it's from a function called get_var props over chain. And I can sort of print it out. And there I go. Got my variable importance. See, well, I said it should sum to 1, and we're about to find out whether I was correct. Okay, good. And I can take that, and then I can just plot the results. So here are the estimated variable importances for this model. Did I get the same picture? Maybe I didn't quite get the same picture. Interesting. I set the seed. Why didn't it give me the same picture? Generally, with these methods, the safe thing to do is to not just run one chain, but run multiple chains, and kind of compare the results across the chains, because there's a non-negligible amount of well, the mixing is not ideal, let's say, and so if you run multiple chains, you might get slightly different results. But these are the estimated variable importances. Of this, I mean, it's a little bit another way to express variable importances using Sobel indices. Yes, there are other ways of doing this. Yeah, there are lots of criticisms, potential criticisms of these variable importances that I'll talk about. One thing that is one thing that's not great. Well, there's a few things that are not great. One is the fact that I actually had to decrease the number of trees. Two, there's a bias against discrete variables, because imagine that you have one variable that's, a discrete binary variable that's important. You only need one split to get that, and so it's not going to necessarily be end up used in a lot of places. Whereas if I have a nonlinear relationship, I might need a lot of splits to get that, and so the nonlinear thing by this measure might appear more important. Does this variable importance method suffer from the same shortcomings of random forest importance, namely overestimating variable importance when many categorical levels are present? This approach, there are a number of problems. Not exactly the same problems that pop up with random forests, but one problem is that if you have a lot of trees, there's sort of a tendency to, so whereas I said you're fine if you send t off to infinity in terms of prediction, you don't want to do that if this is the sort of variable selection that you're looking to get, because the more trees you have, the more chance there is of irrelevant variables sneaking in, and that's kind of the reason that there's this suggestion that was noticed right away in the first BART paper, which is if you take T big and you're doing variable selection, there's a tendency to include a bunch of stuff that maybe isn't important. And their solution to that is to reduce T. In terms of the number of trees, T, is it always fixed beforehand, or is it standard to put a prior on T to have a fully Bayesian method? To the best of my knowledge, no one has been successful at putting a prior on T. Except for people doing theory. Sometimes it's convenient for doing theory, but that's the only place that people have actually done that. So I'm guilty of that, but in practice, no one has. That I'm aware of, and gotten it to work. Right. Yeah, there are shortcomings. Overestimating variable endpoints when many categorical levels are present, I would have to think. I haven't thought carefully about that particular issue, but there are loads of issues. All right. So the problems with the raw variable importance is there's a tendency to prefer. I think variable. All right. So talk on. Okay. Yeah, I would encourage, any interest in this. I actually don't know anything about this, these Sobel indices, although I've kept some eye on it. I think there's something called Thompson sampling also that Veronica Rakova is also proposing for these types of models. But I'll make my pitch for what I think is a reasonable thing to do as well. So there's a tendency to overstate the importance of continuous things because you require a lot of splits. There's also no obvious Bayesian interpretation. There is a Bayesian interpretation for these things, even these variable importances, but it's not obvious what exactly the variable, the Bayesian interpretation of these things would actually be. And the tool that we're going to use to get sparsity into the model or to do the variable selection is going to be to tweak these splitting proportions. So S was the prior probability of splitting on a particular coordinate. And so if I have a decision tree that looks like this, splits on x2 and x3, we had this variable S sitting in the model. And with probability S2, you were going to split on 2, and probability S3, you were going to split on 3. And so the probability of splitting on exactly these two variables, given the shape of the tree, is S2 times S3. And if you choose the S's in such a way that S itself is sparse, then that's a way of getting sparsity into the model. Right. Is there any way to estimate the effect a variable has on the response? So the catch with these models is it can be quite difficult to interpret the variables in isolation. Like if you want the effect of a particular variable, there's a lot of interactions. They're complicated models. The most commonly used tool for getting at that is a partial dependence plot, which I believe is along the same line. So I guess this was only directed to the panelists. I'll read the question. Is there any way to estimate the effect of a variable has on the response, or would something like SHAP or line be needed? Yeah, so all these packages have built into them, except for softBART, they all have built-in partial dependence plots. And which is, for people who don't know what those are, they're kind of a black box way of interpreting the marginal effect of a particular predictor by averaging over all the, I won't go into details about it, but those are outlined in the original BART paper. They do partial dependence plots. But it's a way to get at the marginal effect. because these models are complicated enough that you can't boil down the effect of a variable to just a single, either a single number or a single curve. You can't do that. So the further splitting proportions is a way to bake in sparsity. Imagine that most of your S's are 0. Well, if most of your S's are 0, then all those variables, it's going to be impossible for them to get in. So you can get sparsity in the model by doing that. You could even take, as Joey did with the variance components, you can imagine doing a spike-and-slab prior on these S's. We're not quite going to do that. You can do it, but there are, it turns out, easier ways to go about getting at the same idea. So the packages that I talked about, they let you throw in whatever S that you want. So you can tune that. You can pick whatever S you want up front. And so it turns out that there is a slick way of estimating the S's by empirical Bayes. So you might say, well, I don't know what prior to put on these S's. Is there any way that I can go about just kind of optimizing my way out, just picking the best value of S? And it turns out that what you do is, so let's say you fit the model with a particular default value of S. Then you compute an updated value of your F. So it works out that the EM algorithm update for this is you take the expected value of the number of times that a variable appears, and you divide it by the expected number of branches. And this is all available from output of the models. So this is almost the same thing as the variable importance that, there's a raised hand. I'm going to hit allow to talk. So this is for Sean. Okay. Oh. Ask to unmute. Did Sean have something, or did he put his hand down? Can't really tell. Another question, what does MJ, B, and S on slide 21? So S, that's the prior probability that a given rule in the ensemble will split on variable Sj. That's what Sj is. So remember, there's a prior on the space of trees, and this is the probability that you split on that particular variable. Okay, so that's what S is. Mj is the number of times that the variable has been split on. And B is the total number of branches. So B for branches, total number of branches in the ensemble. S, I guess, for split is the number, is the prior probability of splitting on that. And MJ, I guess there's no, maybe I should have called them CJ or something for count, but that's the count of the number of times that the ensemble splits on it. Okay, so I can do an EM update for these S's, and the S's are encoding the sparsity in the model. This can also be phrased in terms of a map estimation problem. So equivalent to doing empirical Bayes is map estimation under a uniform prior, and you can generalize it slightly by looking at a Dirichlet prior on the splitting proportions with some parameter eta. And the EM algorithm also, you can do it very similar form. Although a neat property of the map estimation is that you actually get exact sparsity. So meaning if you run this algorithm, some of the variables will be completely eliminated from the model. So this is kind of picture of the trajectory of these things as you run your EM algorithm, what happens over the course of the chain. Not the chain, but as you keep fitting these models, running your EM algorithm, what ends up happening? Well, the relevant variables, so in this particular example, there are 5. This is simulated data under a simulation setting that I'll explain a little bit later. But there are, I believe in here, 100 variables, 5 of which are relevant. These are the gray. And the S's for these, as you run it, increase. They're the relevant ones. And the irrelevant variables have importances, or these SJs, decrease. So I become less and less likely as I run this thing to use those variables to split. If you do a math estimation with the Dirichlet, it's very similar, but now you get exact sparsity, so that all of the variables that are irrelevant are eventually eliminated. So the Dirichlet prior seems to do something that's potentially useful. But the question now is, how do I go about picking this eta? So eta is the hyperparameter sitting in this Dirichlet prior. So it turns out that you can. It turns out that the prior on the prior distribution on the splitting proportions is intimately connected with the number of predictors in the model. So Joey chose his prior in such a way to kind of control the amount of sparsity in the model. So he had a beta prior with a p sitting in the second shape component, and the role of that was to kind of keep the sparsity level fixed as you increase your p. Just like that, the prior distribution on S encodes information on the number of variables that you expect to see in the model. So the default setting, so this is what will be done automatically in a BART model. You can show that basically on average, the prior expects that there to be a lot of predictors in the ensemble. So if I have Q variables, Q active variables, and B is the number of branches, the maximal number of variables I can include in the model is actually B. Because B is the number of branches, I have at most B variables that can be included. And you can show that if you assume a prior of this form, that the prior wants there to be a lot of variables included. All right, so a couple of questions. I'll get through this slide and then I'll get to the questions. Alternatively, if you're going to write a prior on some S on the splitting proportions, those have to sum up to 1, and so it's natural to say, well, maybe I'll do a uniform prior. But you can show basically that you'll end up with the same problem of including too many variables. The rationale behind the use of setting a default like this was sort of a non-informative idea, right? Every variable has an equal chance of appearing in each of the branches. But it turns out that this is actually a very informative prior in the sense that you expect a lot of variables to be included in the model. A question: in the easier scenario when all predictors are binary, can you see the problem as a typical variable selection problem, including in model interactions using MCMC? So if everything is binary, yeah, you could. I mean, there is a sense in which these are doing something similar, in the sense that you could grow out a full tree, and that would be the same as a model where all of the individual variables interact. And then by learning the shape of the tree, you're kind of learning how the variables interact with one another. So they're related in that sense. You can write down basically any model that's just on binary variables you could express with a tree. But the role of the additiveness in here, the model kind of encourages low order interactions as opposed to higher order interactions, which I guess you could also get if there were just a bunch of binary variables. All right.
And Tony, just maybe we want to do like I don't know when a good wrapping point up for you. If we can do a break for a couple minutes here before you finish up your slides.
Yeah. Let me. When do I get to code again? I'll try to pound through I don't know if this is a reasonable idea. I'll pound through the next few slides, and then when I get to the code, we can take a break there.
Sounds good.
All right. Shapely value also an alternative to Sobel. Yeah. Lots of alternatives. These are not the, this isn't the only way of doing it. What I will say about these alternative approaches is that the way that they're kind of operating is that you assign the importance of a variable in sort of a heuristic way. So that's true for the variable importances and Sobel indices. They're sort of heuristic measures of variable importance. They're not quite the same as the fully Bayesian, so they're qualitatively different than what Joey was doing with the gammas. And we're trying to move to where we can actually do something that is similar to what we're doing with the gammas within the context of this model. All right. So the prior distribution, and I'll say what S is again, since I think that think of S as being analogous to the gammas in Joey's model. Just if you ever forget what S is, just think in your head it's similar to Joey's gamma, but it's kind of continuous. So we put a Dirichlet prior on it, and a Dirichlet prior of a particular form. So the S is Dirichlet, and this is kind of a visualization of the simplex in 3 dimensions, which is where the Dirichlet is supported. And if you look at the interior of this simplex, so I'm in 3 dimensions, the interior points correspond to points where S is non-zero along all 3 coordinates. So it corresponds to dense models. All of my S's are non-zero. The edges of the simplex correspond to models where one of the variables is 0. So 2 of them are non-zero, 1 of them is 0. So it corresponds to models that are too sparse. And the edges of the simplex correspond to models where exactly one of the S's is non-zero. So it corresponds to very sparse models. And if you look at the Dirichlet prior and you decrease the alpha down, you can see that you're concentrating more and more on sparser and sparser models. So this is like having a sparse prior on your S if you take alpha to be small. And right, so we have dense models for big alpha and sparse models for small values of alpha. And you can quantify exactly how sparse your model is with this nice result that says that the number of variables that you include in the ensemble has approximately a Poisson distribution, and you can compute that distribution, the mean of that distribution in terms of alpha. So this is just a mathematical result that you can establish. It turns out to be very accurate. So if you want to say I want a Poisson 10 prior on the number of variables in the model, my theta then is 10. I can pick my alpha in my Dirichlet prior to get 10. And now I have a Poisson 10 prior on the number of parameters that are included. So it's a little bit indirect, but it lets you control the sparsity just as Joey's approach did. How would the selection behave with binary covariates and interaction with low prevalence, more zeros than ones? I don't see that it should interact particularly. So there are obvious, there are problems with, an abundance of zeros. So if you have very sparse columns of your design matrix, that introduces some problems. I don't think it would. I don't see why that would introduce anything unique beyond the inherent difficulties of having a column that's quite sparse. At least that's my intuition. All right. And a bonus is that this prior that I mentioned turns out to be conjugate, conditionally conjugate. So it's easy to do this in your Gibbs sampling. It's just a one-line change. All right, so illustrations will carry us the majority of the way through. So now is, I guess, a good time for, want to do another 10-minute break?
Maybe just do 5 minutes now, just so we're getting to the end of it, so we don't go long. So you have
Yeah,
time to do your.
Probably folks would rather get out of here than
I think
have an extra 5 minutes.
I think that's right.
Okay. So this is so there might be cases where, all right, MJ is the number of times that the ensemble splits on a particular variable. So if variable 1 appears 10 times, then M1 is 10. Right. Cases where xi times xj is a bunch of zeros. So the what would happen in that case, where you can't actually estimate the interaction, these priors have a preference for models which do not have interactions in them. So if you have a situation where something like that happens, where you can't estimate an interaction, so let's say variable x1 is very sparse, variable x2 is very sparse. If I multiply them together, I just get zeros. So it would be impossible to learn an interaction in that case, right? I wouldn't have any information to learn an interaction. The way that these models would deal with that is basically they just wouldn't estimate an interaction. There's kind of a preference that if there is no evidence of an interaction, or if I don't have any way to estimate the interaction, it will prefer to eliminate. Hopefully that answers the question. Oops, I think I closed something.
That expression for theta was really interesting. It seems very related to like have you seen like the Dirichlet process result about like, how many, mixtures you get out of a Dirichlet process, something like that. That has a very similar form to that.
Yes, yes.
This probably comes from the same idea.
Yeah, it's the same thing. Yeah, where is it?
Yeah.
You mean this form? You're right.
The expression for theta. I haven't seen the Dirichlet process.
This
expression
thing.
in a while.
Yeah.
Yes,
this is also a this type of result has also been proven for like the number of clusters in a Dirichlet process mixture.
Yeah.
So I know that we're just talking here, but I know that there was like that paper by Miller that sort of showed that Dirichlet process mixtures are inconsistent for estimating the number of clusters. There's a neat paper, I think, that showed you can get around it by, you don't have to go to like these other models. You can just take this. You can just you can keep theta fixed instead of alpha. When you keep the theta fixed, it actually works. I don't know. Kind of a neat thing.
It's an interesting point that they brought up about the interactions if they're all zeros. Because like a random forest or like a cart model would never split on that, right? Because if you split it into two parts, there'd be only data in one portion.
Yeah, you would
never make that split. So is it also literally mathematically impossible to make that split here, or is it?
It's not mathematically impossible. So you probably, if you sample eventually, right, the posterior probability of that split happening is going to be non-zero. So like it will appear if you run the chain for, longer than the age of the universe or something. I mean, maybe much sooner than that. But yeah, these things don't really care that much about, like, when you don't have any information, it just kind of is taken care of from the fact that you have that shrinkage prior on mu. Because you have a prior on mu that's shrinking, you know, if I did, let's say, it goes to a mu, that mu gets shrunk to 0. So it's sort of like, and then there's no data to actually show that it's something other than 0. So it's just going to be end up estimated to be 0. Which I guess is kind of, I guess it's not obvious if that's what you want, but I guess I can't think of anything else that you would. Yeah, it's not obvious that you want to extrapolate necessarily to 0, but or that interaction is 0, but I don't know what else you would be able to do. All right, so we'll get back into it. So now we just have some illustrations of this idea. Where do I want to be here? So I'll go to, where is it? Here. So I'm going to illustrate these ideas now using the Big B BART package. I don't know, I'll refresh the R session just to make sure nothing weird happens. So if it's the load up tidyverse, I load up this BART, which hopefully you wouldn't have any problems installing. And then the function that I'm going to look at is function that looks like this. So it's a complicated enough function that things are kind of interesting. So I have an interaction between x1 and x2, nonlinear interaction between x1 and x2, a quadratic term for x3, and we have a raised hand, or maybe they put it down. Quadratic term for x3, and then linear terms for x4 and x5. So this is a complicated enough setting to be actually interesting, and there are 5 relevant variables here. And I'm going to generate, and I'm going to look at a setting where I have 5 relevant and then 995 irrelevant variables. So very, very sparse setting, and we'll just kind of see how this thing works. Right, how do I back here? So these are just code for generating the data. This is a function that evaluates that function, and a function called genData that generates some data for me. And now I'll fit 2 models. So there are 2 models that I'll use here. One of them uses the sparsity-inducing Dirichlet prior. Again, think of this as being making that S vector sparse, which again, think of as being like Joey's gamma. So Joey's gamma is encoding sparsity. Our S here is encoding sparsity. And we're going to use this sparsity-inducing prior. So that's this. Fit Dart is the one that does sparsity. Fit BART is the one that does not use sparsity. I'll fit it. It goes reasonably fast. It's good to have some breathing room. And you see again, it's truth in advertising in me saying that you don't really have to sweat model specification. I'm going directly with there's no hyperprior in here or anything. So I mean, you could, right? If we're being good Bayesians, you know, you can make the prior whatever you want. But for routine use, you don't have to. It's also pretty easy, I think. The default number of trees here, I think, is 50. In case, I mean, that's not obvious from here, but I believe it's using 50. All right, we got our fit. Nice, convenient predict function. Predicting on my testing set and getting the means. All right, so I have predictions on my testing set. So I generated my sim data thing here is just generating data from that model that I wrote down. Generated for me both a training set and a testing set. So the testing set is of size 100. The training set is of size 250, and there are 1,000 variables. And this argument here is just giving me the noise level. I can do the root mean squared error now on the, so this is the prediction from the BART model, and this is the true value of mu, so that's the target. Root mean squared error of about 2, which has no context whatsoever, and so it's not clear if this is good or bad. But the DART model, which is the model that had the sparsity, so the D is actually stands for Dirichlet. I run it here, it has a test set error that's more than twice as, well, more than half as small. I don't know if that makes, half is big, so less than half as big. So this is a pretty substantial gain, right? If you take advantage of the sparsity, you are able to reduce your prediction error by more than half. The following gives just a figure for sort of trying to understand exactly what's going on. So here I have on the x-axis the mean, or the true value of the mean on the testing set. So this is the true predicted value. It's on the x-axis, and then the prediction from the model is on the y-axis. So BART, meaning without the sparsity-inducing prior, this is if you don't do any variable selection, is on the left. And if you do variable selection using the sparsity-inducing prior, those results are on the right. And you can kind of see what's happening. There's a lot more uncertainty when you have 995 irrelevant variables that you're not dealing with appropriately. There's substantially more uncertainty in the predicted values. Although, kind of nicely, it's still, I would say that this is kind of failing, but it's failing gracefully in that these intervals are still kind of covering it close to the nominal level. So that's kind of neat that even if you don't, the absolute worst case scenario doesn't happen. But you gain a lot by taking advantage of sparsity. Both your predictions become more accurate and your uncertainty around the truth becomes correctly more narrow. So that's kind of what's going on here. You can also look at posterior inclusion probabilities. So rather than looking at variable importance, this model actually eliminates directly some of the variables. And if I run it, posterior inclusion probabilities. So this is very similar to Joey's, the pictures that Joey showed you for the linear model, having a posterior inclusion probability and for all of the variables. And the green ones are the active variables. it's hard to see that there are actually 5 of them up here because there's 1,000 variables along the x-axis. But the red ones are irrelevant, and the green ones are the 5 relevant ones. And so you can see BART does a good job of picking out the 5 relevant ones. So if you don't include sparsity, you do pick out the 5 ones that are relevant. So that's pretty good. But you have a bunch of, you're wasting a lot of energy on these irrelevant variables, the 1,000 irrelevant variables. And you do get a few false positives. If you adopt 50%, let's say, as the cutoff for being worthy of investigation, you do have a couple of false positives.
We got a question, the question answer about how DART does when there is no sparsity in the underlying model.
Yeah, so when there is no sparsity, it depends on what you do. The prior that's built into this particular package uses a prior which is designed to adapt to a lack of sparsity, meaning that, you know, so Joey had this parameter tau in his model. He put a prior on it, and you could ask a similar question: what happens when the model is not sparse? What happens? And what you would expect in Joey's case, depending on the prior that you put on tau, what you would hope is that if the model is not sparse, then tau is big, let's say close to 1. And that will kind of help you out, right? It'll let you revert back to a case where the model is dense. And you can do something similar here. And the idea, I mean, if I go back to, you know, this expression for the prior on the number of predictors, you can imagine if I put a prior on theta that allowed for very large values of theta, then I could kind of, you know, hope to do well, even if there is no sparsity. I should expect to do, well, I should hope to do no worse than BART. So I should hope to, if there is sparsity, benefit from it. And if there is no sparsity, revert to the performance of BART. It's probably mathematically impossible for a method to, you know, there has to be a trade-off. You can't accomplish both of them perfectly. But the prior is designed to kind of do that. So
I think this is an interesting discussion, actually, and I think it doesn't just relate to the DART, like the BART stuff that we're talking about here, but I think it, you know, Tony, you're kind of alluding to it, that the previous stuff we covered in the first half of the course, there's a paper, and I'd have to search hard to find it because it's been a long time since I read it, but they sort of showed that if you, in these situations where you use, say, like spike-and-slab priors, and I think it's happening in this DART model as well, is that if there really is no sparsity, like Tony said, the tau tends to grow, and what you end up getting is that you don't really remove any variables from the model, but then the shrinkage from the slab prior acts as like a ridge regression type shrinkage. So you can kind of get two extremes with these spike-and-slab models, is that you can get one extreme where you have a high degree of sparsity and it really removes everything through that tau and through the spike at 0, but if there's not a lot of sparsity, then you don't remove very many models, but you end up shrinking all of them towards 0 more aggressively, like a ridge regression would, which could be useful.
Yeah, and the to make the point that there is a trade-off, to get that kind of behavior where tau grows requires that the prior put enough mass at the high values, which the beta prior that Joey wrote down does not do that when p is large. So it's kind of like a, you know, but there are very good reasons for doing what Joey did. If you do a uniform prior, there are issues with that as well. And so there's not like you can't have it all. And there is a theorem that says you can't have it all. So not about BART, but just in general, you can't have it all. But you can try to get close, right? By doing something adaptive. In this case, I mean, I have some simulation. You know, I've done some simulations with this. I mean, you usually don't make it worse if it's sparse, or if it's not sparse and you do this, you usually don't make it much worse. You might lose a little bit, but it's usually not a catastrophe. Whereas, I mean, I would say this while BART is kind of okay here, to me, you're leaving a lot on the table, right? All right, but yeah, so this is variable inclusion, and you can't see what's going on here around 0 with the 5 relevant ones. So if I just zoom in, you can see that there are 5. It picks out the 5 relevant ones in either case, and but how they deal with the irrelevant variables is quite different. If our 5 relevant variables are factors, does BART-DART tell us which levels within those factors are more influential relative to the others in predicting the response? So yeah, this is a sticky issue with BART, if I'm being honest, because the reality is that all of the implementations do a one-hot encoding of any categorical variables. They do a one-hot encoding, meaning they add a separate column. And that's good in the sense if you expect that one of them is driving the response, you will be able to see, like, okay, this is the particular factor level that I'm splitting on. You don't necessarily want to do that. You don't necessarily want to do one-hot encoding with categorical variables in decision trees. You might want more exotic sets. So imagine if I have 4, I might want to be like, if your factor level, if you're blue or green, go left. If you're red or yellow, go right. I might want to do something like that. The implementations of BART don't let you do that. But you could. Now about specifically importance, when you do these sparsity priors, when you're doing categorical variables, the correct thing to do is to share, all of the, if I have different factor levels, they should all be using the same S. So if they were in Joey's case, they would all have the same gamma, most likely. That's not so informative about particular levels of the factors, but there are other ways you can try to get a handle on it. All right. So we're in the home stretch here. I sort of suspect we won't get through everything, but that's okay. Through all of this variable inclusion stuff. So this does have an interesting effect if you include sparsity in the model on, where is it? To here. In addition to doing this sharp variable selection, you do get some kind of interesting behavior in terms of the variable importances. So I will run this real quick. Run. So I'm just revisiting the Boston data, seeing how these variable selection techniques, what impacts they have on the things that, on the variables that we look at, on whether things are important or not. And you can see, I would say that when you do it without the sparsity, I'll zoom in, or I'll go back to the results here. This is, so these were the results for the variable importances when there are no sparsity. And one of the problems that I have with these variable importance measures is that it's not quite clear where the threshold is. And so if you compare that to what you get if you bake sparsity into the model, you can see that it's actually now genuinely eliminating some of the variables. So zone, ZN, this is one of the variables in the model, gets dropped entirely. And there's more separation for the things that definitely matter. So there's distance, LSAT, these variables up here with large importances, they very clearly matter. And some of these other variables, which don't matter, the shrinkage kind of lets you more easily distinguish what's relevant and what is not. Okay, so and I think I have posterior inclusion probabilities here. So if you fit the model with this, the posterior inclusion probability basically says everything is relevant except for these two variables. This is for being close to the Charles River, and this is the Zn variable for the data set. Can't. That's something to do with, well, I guess I can look it up. I'll have to speculate. So Zn is, where are you? Proportion of residential land zoned for lots of over 25,000 square feet. So I guess it's whether you're zoned for being a business district. Right. So those two were eliminated, Charles River and the zone. But you can also look at how you can see just what happens in terms of prediction accuracy and whether you use the DART or not. So I guess there's two questions. One, do you gain anything by using DART rather than BART, meaning the Dirichlet prior? Two is, do you lose anything, I guess, which is almost the same question, but related to the question, what happens when things are not sparse? This doesn't seem like a very sparse setting, and so you might be worried that by imposing sparsity, maybe you actually lose some prediction accuracy. So I'm just fitting the model, I'm fitting the DART model, and I'm fitting the BART without the variable selection, and evaluating it on some test data to see what will happen. Then after that, we'll look at explicitly eliminating those two variables that were deemed to be irrelevant. So as far as correlation on the testing set is concerned, there's not a big difference. So that's arguably a benefit in that you get some additional variable selection, and you haven't given up much in terms of prediction accuracy, right? It's not clear that this is a statistically significant difference, but you're using a more parsimonious model. In terms of the variable selected, if you don't do anything with sparsity, BART will just pick every variable gets included, right? All variables are included all the time, versus if you use a sparsity-inducing prior, you eliminate. In this case, it eliminated. Well, I did a data splitting thing, so it's not going to be exactly the same result, but it eliminated zone, Charles River, and actually this measure of whether the land is industrial or not. If I explicitly eliminate those two variables that we identified as being irrelevant and fitting a BART model, you can see it. You basically don't lose anything by doing that. Go back to here. Yeah, so if you just straight up eliminate those variables, and we use the DART model to figure out that those were the things to eliminate, you can see the correlation is basically the same as the other models. It's even a little bit higher than the original BART model. Is it true that the code wouldn't run without first having installed DART machine? You do need to install the package, that is true. Yeah. This would not run just with BART machine. You have to be using, because the sparsity prior is not built into BART machine. How well do these methods perform with collinear predictors with strong signals? I mean, that's a hard problem in general, I think. Yeah, I mean, there's all kinds of issues you can run into both with the linear models and with the models that, or sorry, even with the linear models when you have strong collinearities. What tends to, so I've tried some kind of very sort of perverse settings where, you know, something like a correlation of 90% or something. I look at it in a paper where I do this. There's a setting where we looked at very high correlation. And I think you do about as well as you have any right to expect to be able to do, meaning that you're, you know, it's hard. I mean, it's a hard problem when you have strong collinearity. But you're kind of okay relative to other approaches. I mean, it's worked surprisingly well for me. Although I mean, there are some special things you might do in those situations. So one thing, if you have like extreme correlation, rather than putting a prior on S, you might anneal. So if you take that alpha and the prior, you can anneal it down to 0, and that can give you a little bit additional stability. Because then it's kind of like you're starting in this non-sparse setting and working your way down. So, you know, but it requires special consideration because it is a difficult problem. All right. I'll close with interaction detection. I mean, this is all, yeah, I mean, I think I don't want to keep people here too far. Again, I don't want to push my luck with people's patience, I guess. But a neat thing you can do is that this does do interaction detection as well. For a Boston data set in particular, I'll just close with illustrating this point, and then we'll call it a day. There are interesting interactions in the Boston data set. This is a figure that is in a paper with me and one of my students, where we identified a particularly kind of interesting interaction in this data set between the variables LStat and DIS. So LStat is the number of, or the proportion of people in a suburb which are lower status. That corresponds to, I believe, things like income and things like that, like what's the income of the people in the neighborhood. And then there's distance, which is how far are you away from the industrial centers of the city. And typically what you expect is if you're right in the middle of downtown, those properties are going to be very expensive. So there's another suggestion of mutually exclusive groups of predictors. We have I have a paper that does that in a genomic setting. So exactly the situation that you're talking about, where things are very highly correlated. Maybe it's full of sound and fury signifying nothing, but I don't know. But yeah, so it is possible to do that. But yeah, so you expect if you're in the middle of downtown that your houses are, any residential area is going to be very expensive. But it's sort of a non-monotone relationship in that if you have people who are lower status in the middle of the neighborhood, then actually the price goes down. And it's probably due to things like rent control, right? Like the only way that people who are lower status could afford to live in a place that is, in the middle of downtown would be if there was some cap on the rent or something like that. So there's probably a substantively good reason for this relationship. You see, like if it's a lot of lower status, then things actually get cheaper as you go into downtown. Whereas your higher status, prices go up. Definitely there is an interaction there, and you can tease it out using this package. Interaction. The way that these interaction need to restart. The way these interaction detection ideas works. It's the same idea as the variable importance, where now you say an interaction is important if it shows up a lot in the model. So rather than just looking at a single variable, you say that an interaction is important if there are a lot of trees that essentially split on both. So you can get for every interaction, and it'll take a little while to fit this. It's a little bit more expensive to get the interactions. But I'm running this interaction investigator and basically telling it, I want to look at the top 10 interactions in the data set and see what it finds. I believe that this particular thing is doing some sort of permutation test. So it's like permuting columns and things like that. Try to get at these interactions. Or maybe it's just averaging over them, running multiple chains. This paper does something a bit fancier than what the package is doing, but unfortunately there's no software for what we implemented in here. Yeah, so here are the interactions, and you'll see it picks out exactly that interaction as being much more important than the other ones. So this is not great in the sense that it doesn't give you statistical significance or anything like that. It doesn't give you a meaningful posterior inclusion probability. Nevertheless, I think if you looked at this, you would say, okay, one of these interactions clearly pops out more than the other ones, and for good reason, right? There's definitely an interaction between these two variables. All right, and there's no great way of doing fully Bayesian variable selection for the interactions. There is an attempt. It's in this paper, and you can look at the end of the slides if you want to look it up. But there's no software. And I guess I'll skip this other material, which is really great stuff that Rob McCullough and a few other people have been looking at, just for the sake of giving you all a break. So I'll close with just some pointers to some other places, which is where would you go for theory for these methods? There's a lot of really great theory for linear models. So things like establishing variable selection consistency. There's this Castillo paper, Scott and Berger, a classical paper. Another really good paper in the context of linear models is this paper by Liang and others. That paper focuses a lot on this specification of the prior on what Joy was calling sigma squared beta. How do you go about doing that? What are the various approaches for doing that? There's a theory for BART models, both for variable selection and for prediction, and in sparse settings. So if you want theory, there are a couple of theory papers for you, and as well for additive models. And then there's a whole other class of things we didn't talk about called continuous shrinkage priors, the horseshoe prior being probably the most popular one. A lot of papers on that. I think the Carvalho paper is probably the most cited of them. And all the extensions to GLMs, basically they all use this Albert and Shib trick or some variant of it. So there's for probit models, you do this. There's a Polya gamma trick for logistic regression if you want, and then other approaches for other sorts of models. Yeah, summarizing, these models are really easy to use, good for prediction, works well under sparsity if you use the Dirichlet prior, and there's lots of tools for variable selection, although not as quite good tools, but useful tools nevertheless for interaction detection. And these are just the references you can pull those from online. And yeah, that's all I have to say.
Awesome. Well, yeah, that was great, Tony. Thanks. And thanks everyone for coming. Yeah, this has been great. Super interactive group. A lot of people here. a lot of great questions. So thanks everybody for coming, but I think we'll wrap up. And again, these are all going to be posted on the conference website if you want to see the recording. But again, thanks for everyone for coming.
Well, there are any questions at the end, we'll stick around for a few minutes for any questions.
Yeah, we do have one. Sean has a question here.
Yeah, on the ballparking runtimes for BART on massive data sets. If you have a data set that big, and BART has been applied to very massive data sets, but they are exclusively, you know, they basically exclusively have to use distributed computing to do it. Yeah, there's this paper on consensus Monte Carlo, and one of the examples, it's like from 2010, one of the examples is BART. So I guess they implemented this over at Google of trying to do these on massive data sets, and they used consensus Monte Carlo. 150,000. Now, naively, it should be linear in the number of samples because you only have, so if you just look at the computational complexity of a single update, the only place that n comes in is in the likelihood evaluation, and it comes in linearly. So the actual computational complexity, if you think naively, per Markov chain iteration should be of order n times t. T is the number of trees, n is the number of samples. The issue is like when you get to these big sample size, it wants to grow bigger trees. And so because of that, you have this, it becomes hard to make a sharp prediction of how the computation scales because of that. Because the computation actually gets harder and harder as you get more data because the model wants to be more and more complex. So it depends on the rate at which those trees are getting deeper. If that, so it's like, short story, it's like, it's hard to make exact predictions, but people usually don't do 150,000 without doing some kind of parallel sort of thing. Hopefully that answers. I guess if I did, how big is this Boston data set?
Like 500, isn't it?
Yeah, it's not very big. 500 and what's 150,000 divided by 500? 300. If you have 300 machines, I guess it should take the same amount of time. There are a lot of issues with slicing and dicing data like that too. This is there is a fantastic recent development on what's called XBART. So this is like an attempt to scale up BART to these very large data set sizes. And that runs on scale after accounting for tuning parameters. I'll see if I can. I probably should have referenced this paper. It's by, I'll just Google it. Should be appearing in JASA, I think. Yes, this paper. This paper is the best approach I know of for dealing with BART at that kind of scale. It tries to get to XGBoost levels of speed, hence the X at the beginning. They do look at some very large data sets in here. All right.
I do not know if this is computation time, though. I can't speak to like the really huge data sets, but in terms of like a really flexible Bayesian approach, I think one reason why BART has become so popular and some of these extensions that Tony's worked on to increasing sparsity, they tend to run pretty quickly, I've found, relative to other highly, like if you wanted to fit a Gaussian process, the computation would be horrible, whereas these things can be fit relatively quickly. So it's hard, I guess maybe, the big sample size is one thing, but just overall as a computation time thing, I think one reason why they become very popular is because they can be fit so quickly.
I've heard simultaneous, like, I've been in rooms where I talk to somebody and they're like, oh, I can't use BART because it's too slow and I have my problems. And then like 2 minutes later, I'm in a conversation with someone who says, oh, BART's great, it's so fast. So like it really depends what your perspective is, because if you're coming from a world of XGBoost, yeah, these are much slower, although this XBART stuff has some prospect of matching it in terms of speed. But if you're doing Gaussian processes, I mean, come on, this is light years. That's not a measure of time, but
someone who works at Google, you know, might think this is slow.
It's much better.
But you know, for most of us that are used to using Bayesian approaches, I think that this is not terribly big issue.
And there is a question about
Hamiltonian.
Hamiltonian Monte Carlo. That is if you can figure out how to do HMC on spaces of trees, let me know.
Go for it.
That would be fantastic if there's a way to do that. Hamiltonian Monte, what you would want to do is, Hamiltonian Monte Carlo is great because it's making sort of intelligent proposals for your Metropolis Hastings updates by following the gradient. But if you're trying to fit a tree, there's no natural notion of what the gradient is. But there are ways of trying to make sense of doing Hamiltonian Monte Carlo on discrete structures. And I leave that to people like, Michael Betancourt to figure out how to do that. Because the mathematics are probably extremely deep, but that's I think it's much harder. Believe me, if someone comes up with that, I will be a way to do that works. I will be the first person to implement it in my stuff.
I don't actually know if this is why this is the case, but some of the like Stan, which is uses a lot of Hamiltonian stuff, doesn't handle discrete variables very well.
Yeah,
and I'm not sure if that's due to this issue of it's difficult to use HMC with discrete spaces or not. But that could be an issue.
If you ask them, they will say things like that. They just don't have a good way. They don't have a way of doing it that they believe in. I don't want to speak for them, but I think that's what they would say, that they don't have a way of doing it that they fully trust.
Tony, do you wanna? Someone asked about the prior on T again. I put in my thoughts on it, or brief thoughts. I don't know if you wanted to add anything. DTR asked it's in the chat, not the Q&A.
I tried it, and the only thing I can say is that my predictions got worse. I never got to the point of figuring out why things were going wrong. I just noticed that my predictions were getting worse when I did it. So
I think that my experience with, not so much with BART, I think BART has a similar structure, like with random forests or bagging or whatever. I think it's a little bit more obvious in those settings, but adding more trees isn't going to make it worse. And I think Tony touched on that with T here, because of the kind of regularization by letting the variance be a function of T, that you don't really do any worse by just setting T to be big, right? So you don't stand to gain much by letting there be a prior on T, right? There's not much to gain, but you can do much worse in terms of sampling, and it makes it much harder. But you don't, just as from a model perspective, you're not going to gain much by doing that, right? It's not even clear that there's an ideal T value that'll do so much better than other T values, right? Which is one reason why you want to do that, is to specify prior on, is to find the optimal value. But I don't know that there is such a clear optimal value in this case.
Yeah, T does have, there is some interplay between T. So I would agree, setting T large isn't such a big deal for prediction, but it can have some issues with the variable selection. So for that reason, they set T small in the initial studies, the initial BART papers, because they found if they took it too big, the predictions got better, but the variable selection got worse. And so one of the selling points of the Dirichlet stuff is that it lets you use a big T even when you want to do variable selection, because if you don't use it, then you have to set the T smaller. And that paper discusses the reasons why you have to do that. So question about cross-validation. you can do cross-validation, and that is one of the things that you can tune T using cross-validation. Actually, the optimal value of T for the simulation I set, I used like 200, but actually the optimal value was like 10 or something. So I overkilled it on the number of trees. But yeah, I mean, cross-validation is great. It doesn't always make things better. So like you can get some counterintuitive results where the default outperforms cross-validation. It's not as weird as it might seem, because when you move to test data, there is some, there's still some extent to which you might be overfitting by doing the cross-validation, because you're tuning all these parameters using the training and the validation. Sometimes the defaults actually generalize better. But I think I would always use cross-validation if I had the patience for it. I'm just, I don't know. I'm like, I'm like reckless. I just throw in the defaults and I never think about it again. And yeah, I mean, you could criticize me for that. You probably and I have been punished. HMC for spike and slab. You can do that. For the spike and slab, there's for the spike and slab, the betas usually they have a nice full conditional, and so there's less of a need to do something like HMC. Or if you were extending it to a probit, where you might do data augmentation, again, there's a nice, clean, full conditional. So if you have the full conditional of the beta, there's less of a need to do something like HMC. But you can. There are settings where something like HMC would be useful for that. Like with these continuous shrinkage priors, people do that.
Yeah, so I don't know if the question also was referring to possibly using it for the gammas, but I think as kind of the same reason we discussed with the tree-based models is that that's not really very well worked out. There's not a good way to do that, I don't think. Somebody's freezing. I don't know if it's me or if it's Tony. I'll move to the other room.
That's probably me. Did we miss any questions?
No. Give it another second, see if there's anything else in there, but. Now we can see how many participants are left in there, which are the people who fell asleep during our presentation. Yeah.
Let's see. We have a survival curve that we can estimate.
Yeah.
I can use a BART model to estimate.
Yeah, there
if
you
I
go.
just collect some features on these people, I can fit a BART to estimate their hazard rate.
Oh, got some more questions though. One is about Python code and one is about recent challenges in BART. So I'm guessing, I don't personally use Python. I know it's very popular and I have used it, but I don't use it regularly. It's very popular in industry because it's faster. I'm guessing BART has an implementation in Python, but I actually don't know if that's true. Tony, do you know if that's true?
There is one. There's at least one. I've never used it. It's not in scikit-learn or anything like that. I haven't used it, so I can't comment on it. I just know that various students who like to use Python have used an implementation in there. Recent challenges in BART. There's a lot of great theoretical challenges, but well, that's probably not worth discussing. But things like proving Bernstein-von Mises theorems are super interesting, to me at least. Scaling it is a big challenge, and there is this XBART thing. Whether that's perfectly applicable or not, I don't know. Like how ideal of a solution it is, I don't know. Yeah, that's what I mean. I guess if I said what would make me the happiest if someone cracked the problem of, like, if I had to pick one problem that someone could just solve for me, it would probably be sampling quickly from the posterior distribution or scaling it. That could be, you know, someone being very clever and figuring out how to do HMC on these things. It could be some other innovation. That would make me the happiest. These models are actually quite easy to extend to other settings, though. So if it's like, I want to build a model for XYZ, a lot of the packages, it's very easy to just drop it in. Like, you don't have to. So that's kind of a distinguishing feature between my material and Joey's. Joey kind of was presenting things in a way where, like, if you're a PhD student, you can take his stuff and you can start coding it up into your own models. Whereas with the BART stuff, it's, you know, it's difficult to code these things up yourself. But there are packages that you can use that will let you, if you're, say, working in R, embed them in your own model. Just having an object sitting around that does a Gibbs sampling step for you and storing the trees somewhere else.
Yeah,
outside
that seems
of
to
R.
be. So one area of research that I work in a lot is causal inference, and causal inference, BART has really kind of exploded in the last few years, and it's been shown to work really well in some like data analysis competitions and stuff like that. But I think, you know, the main reason is I think people in causal inference are not that familiar with Bayesian approaches and Bayesian nonparametric approaches. I think they think that BART is like this amazing, you know, all, you know, solves everything model, and I think that's not really the case. I think other nonparametric Bayesian methods could do probably similarly well, but it's so popular because it's so A, fast, and B, it's like Tony was just saying, is it's really easy to embed it within other models, right? Like within whatever you want to do, you can, the existing software sort of lets you embed that within your whatever you're doing quite easily, which is why it's become so popular.
There are reasons to expect it to be a little bit to do better than some of the other Bayesian nonparametric approaches. In particular, the preference for additivity. So if you're thinking about a causal problem and you have a lot of confounders, you might not expect that most of them interact with each other, and that's something that BART kind of hits that middle ground where you allow for interactions, but you don't encourage interactions. So like a GAM, no interactions. A Gaussian process fit kind of nice, you know, just with a multivariate kernel, tons of interactions. And BART kind of lets you, it gives you a knob, you know, it gives you something in between that lets you do something. And there are ways to make that sort of intuition precise. But I feel compelled to defend BART, even though you're probably right that lots of other things could be made to work.
No, I mean, I think you bring up a good point about it being a nice balance, and I actually didn't know that result. Maybe I'd heard of it, but that result that you said about the number of trees goes off to infinity, that you get a limiting Gaussian process, and that might kind of hint at this thing that you're talking about, that it's similar. It gives you a lot of the same flexibility, but it's a maybe slightly less, you know, flexible. But it's a nice middle ground where it's also computationally fast. It gives you a lot of flexibility. Doesn't give you these, you know, extreme interactions like you just said if you throw a Gaussian process with a bunch of covariates in it. So it's kind of a nice middle ground that is both good as a middle ground from like a statistical point of view, but also from a computational point of view.
Yeah. And I think that's, I mean, the truth is the reason it's so popular is that the software is really good. Like, people put a lot of love into it. And there isn't, as far as I know, comparable stuff for, I mean, you can do Gaussian, you can do all the stuff in R, but it somehow seems to always be a little bit more brittle than the BART stuff.
Any other questions? Stick around like another minute. If we don't have another question, we'll close up the show. Hey, that's a question. You're welcome. Thank you for the questions.
Stop sharing. I've given Richard enough free publicity.
All right,
So
seems
well
like
done. So second cross survived.
yes, I think we're all